Good morning to one and all dignitaries, distinguished alumni, faculty members, and dear students. Thank you all for joining in our workshop on recent progress in astrophysics, a tribute to Professor Emin Saha, which is happening in a virtual mode. It is my pleasure to walk you through the workshop and introduce you to the speakers and delegates that have come from all over the country today to share their knowledge and enhance our mental horizon. So with this noble thought, let us start this evening by lighting the lamp in front of Goddess Saraswati and by doing Saraswati Vandana. Goddess Saraswati is a symbol of knowledge, music, art, wisdom, and nature. May the divine power bless us all.
या कुन्देन्दु तुषारहारधवला या शुभ्रवस्त्रावृता या वीणावरदण्डमण्डितकरा या श्वेतपद्मासना.
Okay, so now I'd like to call Professor Suresh Chandra. Professor Chandra is a Deputy Director of Amity Center of Astronomy and Astrophysics, Amity Institute of Applied Sciences, Amity University, Noida. He is a Fellow of Royal Astronomical Society, London, Fellow of Alexander von Humboldt Foundation, Germany, Associate Member of Third World Academy of Sciences, Italy, Fellow of Maharashtra Academy of Sciences, Pune. He has scientific research collaborations with the scientists in USSR, now in Russia, and Germany, France, and Poland. He has written 17 textbooks, 187 research papers in reputed research journals. 11 students have been awarded PhD degree under his supervision. And work of his 2 PhD students are still in progress. He has completed successfully 17 research projects funded by various scientific agencies. Sir, I would like to invite you to give your opening remarks.
Thank you very much. Am I audible? Hello?
Yes, sir.
Yes. Okay, very good. Very good morning, one and all. Thank you very much, Sefali ma'am, for giving my introduction very nicely. Extremely respected Honorable Founder President, Dr. Ashok K. Chauhan, sir. Honorable Chancellor, Dr. Atul Kumar Chauhan, sir. Honorable Vice Chancellor, Professor Balvinder Shukla, ma'am. Honorable Dr. W. Silva Murthy, sir, President of STIF. Honorable HY AIAS, Professor Sunita Ratan, ma'am. Honorable HOD Physics, Dr. Ashok Kumar, sir. Distinguished invited guest speakers, respected colleagues and staff, dear participants and students, ladies and gentlemen. On behalf of the organizing committee and myself, I take privilege to welcome you all on this occasion of one-day workshop on recent progress in astrophysics, a tribute to Professor Emin Saha, being organized by the Department of Physics in the Amity Institute of Applied Sciences, Amity University, Noida campus. Dear all, organization of this workshop could only be possible because of full support, encouragement, guidance of our Honorable Founder President, sir, Chancellor, sir, VC ma'am, President STIF, sir, HY ma'am, HOD, sir. This workshop is tribute to a great scientist, Professor Emin Saha. Dear friends, information about the distant stars is received through radiations coming from the stars. Astronomers were facing big problem for the long time for classification of stars on the basis of radiations received from them, that is on the basis of spectrum. Professor Saha derived a formula known as Saha ionization equation, and that solved the problem of astronomers which was faced for the long time. This is a big contribution of Saha, otherwise we could not classify the stars in absence of that formula. Friends, the aim of this workshop is threefold. One is to have collaboration with the institutions in India and abroad in the field of astronomy and astrophysics. We are two members in astronomy and astrophysics, Dr. Chanjeev Konar and myself, Suresh Chandra. We are putting our best efforts for teaching and research in astronomy and astrophysics. We are collaborating with various institutions in India and abroad and visiting those institutions regularly. Second aim is to tell about the activities going on in astronomy and astrophysics in Amity University, a kind of report card. The third aim is to tell that we are entertaining queries from students and public. For example, one student asked me, we are living on the surface of the earth and the earth appears as a flat, then how the spherical shape of earth is obtained? We answered the query and also pointed out that this discovery was made long time ago, about 2,500 years ago. And at that time, the technology was not advanced. Further, when we talk about the astronomy, astrophysics, the students or the common public thinks about astrology. And they ask queries, they ask many questions about the astrology. We are trying to explain what is the astronomy, astrophysics, and what is the astrology. In this workshop also, we have put some information about the astronomy, astrophysics, and about the astrology. That lecture is being delivered by me. As far as the report card of the astronomy, astrophysics in Amity University is concerned, we jointly with Dr. Konar have published 55 research papers in 7 years in various research journals of repute. It is pride to mention that one of the papers of Dr. Konar published in collaboration of Professor Anand Hota, who is one of the speakers today, has been published in monthly notices of Royal Astronomical Society. That paper has got a special recognition, and for that paper, the Royal Astronomical Society in UK and NCRA GMRT in India have given the press release separately. There is international project named Square Kilometer Array. India is member of that. Our university is now a regular member of the SKA India consortium, where Dr. Konar is our representative. In Indian SKA consortium, Dr. Konar is also member of Science Working Group and is member of Outreach Committee of the SKA consortium. We are looking forward for more involvement of Amity University in the SKA sciences. Today we shall listen very good lectures about the SKA also. Dr. Konar is also involved in various science popularization activities in collaboration of Nehru Planetarium and Indian first science citizen organization, Read at Home. He is working very lot about the contribution in astronomy, astrophysics, and trying to bring the name and fame to our university, Amity University. If I come to my part, besides the publications of a large number of papers and teaching in astronomy, astrophysics, I have written a book on elements of astronomy, astrophysics. After having good response of that book, the second edition is coming, and that is in press. I hope by next month, the second edition of the book will come. I have written one more book about the beauty of our solar system. That book is also in press. I have published, I have completed 2 research projects, one funded by the Indian Space Research Organization, Bangalore, and one project funded by the Department of Science and Technology, SERB, New Delhi. At present, 2 students for PhD work are working with me. Currently, I am president of Physical Sciences section in Indian Science Corps organization, and that meeting of the next meeting of the Indian Science Organization, Indian Science Congress is scheduled in January 2023 in University of Nagpur. And that meeting is generally inaugurated by our Honorable Prime Minister of India. On behalf of the organizers committee, I am very happy that our distinguished invited speakers are not only contributing, but they have joined the inaugural session also. Without any preference or any name, I would like to name, there is Professor D.J. Saikia, former distinguished professor of NCRA and at present professor in IUCA. Professor Dipankar Bhattacharya, distinguished professor of IUCA Pune, and at present he is on deputation in Ashoka University, Haryana. Professor Pritam Kumar Das, I am thankful that he has joined from Bangladesh. Professor Anand Hota, I have mentioned that he has been co-author in a very good paper of our colleague Dr. Chanjeev Konar. Professor Patrick Das Gupta, he has a class at present in Delhi University. He is senior professor, and because of the class, he could join this inaugural session. And there is Professor Yashwant Gupta. A special welcome to Professor Yashwant Gupta. He is director of NCRA GMRT. In spite of his meeting, he has joined the program inaugural session. All of them have very big contribution in the field of astronomy, astrophysics. Friends, besides the lectures by these distinguished scientists all over the India and Bangladesh, we are having 2 quizzes. The second quiz is after the valedictory session. Participants are advised to participate in the quizzes for getting the participation certificate. Depending on the response of this workshop, such events may be regularly organized by the institution. For this workshop, more than 900 participants have registered. Let us hope large number of them will join this workshop and they will participate in the quizzes for getting the certificate. I hope the participants will join the workshop, and I request the participants to make the workshop very interesting by asking the questions through the chat box, and we will request the invited speakers to answer their queries. I hope they will answer your queries. With these words, I once again welcome one and all. Thank you very much. Thank you, ma'am. Over to you.
Thank you, sir, for such remarkable words. It's always been a pleasure to hear from you. So next, I have the privilege to invite Professor Dr.
Good morning, HY ma'am. Good morning.
Good morning, sir. Good morning, sir.
Yes, so next, I have the privilege to invite Professor Dr. Sunita Ratan, Director, Amity Institute of Applied Science and Chairperson, WRPA 2022. She has held many administrative and academic positions throughout her career. She has a rich, diverse experience of 25 years in academics and research. She has published more than 60 research papers in reputed international journals and has filed 15 patents, out of which 3 are granted and 3 are in pipeline. She has edited a number of books and has contributed chapters with a publisher like Royal Society of Chemistry, Springer, Nova Publishers. She has funded projects from reputed funding organizations, including DRDO, DST, IUAC, BRNS, SERP, and 2 from international agencies such as Interatomic Energy Association, Austria. Professor Ratan has supervised a number of students from their PhD programs, and in addition to her above assignments, she is serving as a secretary, Asian Polymer Association and Society for Biomaterials and Artificial Organs, Delhi. She is a fellow of Royal Society of Chemistry, London. Ma'am will give us introduction to the workshops. Over to you, ma'am.
Yeah, thank you so much, Dr. Shekhari. Honorable Vice Chancellor, ma'am, Dr. Balwinder Shukla, respected W. Selvamurthy, sir, President, STIF, Dr. Suresh Chandra, Deputy Director, Department of Astronomy and Astrophysics, Dr. Chiranjit Konar, HOD, Dr. Ashok Thakur, HODs of other departments, Dr. Sangeeta Tiwari, Dr. R.S. Pandey, Dr. Christine, Dr. Seema Garg, Dr. Mandeep Mittal, and Dr. Dheeraj Pawar, all the faculty of Physics Department and Chemistry Departments, and most important, the students. I welcome you all to the workshop in Astronomy and Astrophysics. one of the oldest branches of fundamental science. We are very grateful to our eminent speakers who have given their consent to deliver the talks. Professor DJ Sekia, Professor Ananda Hota, Professor Pritam Kedas for morning session. The galaxy of speakers also include Professor Yashwant Gupta, Professor Patrick Das Gupta, Professor Dipankar Bhattacharya, Professor Suresh Chandra. I think all the names itself show the importance of astronomy and astrophysics. Actually, we are thankful to our founder president for his unmatchable vision. He established the Center of Astronomy and Astrophysics so that the students are exposed to this important branch of science. We do not have this center in many universities, but Amity Universities, because of the vision of our founder president, was the first private university to establish the Center of Astronomy and Astrophysics. And till then, our students are benefiting a lot. They are doing this course as an elective course. They are including this course. Even the students from mathematical backgrounds are also interested in this course, and they are learning and they're exploring the mysteries of astronomy and astrophysics because of this center. We are thankful to Dr. Suresh Chandra and Dr. Chiranjeev Konar, who are taking this ahead with all the courses, designing the courses, giving all the facilities to the students to learn this course. This online workshop is meant for anybody in order to disseminate the knowledge of fundamental science and difference between astronomy and astrology. We all know that India has a rich history of knowledge in various branches, including astronomy, and it's in a great position when it comes to astrophysics in research. We have giant meter wave radio telescope, GMRT, which is built and operated by NCRA TIFR in Pune. We have AstroSat, built and operated in ISRO and other institutes. Devasthal Optical Telescope, built and operated by Ares Nainital, and Himalayan Chandra Telescope in Hanle, Ladakh, built and operated by Indian Institute of Astrophysics, Bengaluru. For this workshop, we saw enormous participation. Registration has been done by the college students, PhD students, faculty members, and professionals from all over India. Moreover, people with educational background other than science also participated. So this tells about the interest in the astrophysics, the people are astrophysics and astronomy, the people are having. For the students of all level, faculty for all level, this workshop is going to be very useful if they wish to pursue career in this field. They will have from this workshop, they will get good exposure of various possibilities, whether it is career opportunity, whether it is the research opportunity, whether they want to do something in astronomy and astrophysics. This is what the aim of this workshop is, to make everyone aware of the beauties of astronomy and astrophysics. And we recognize the enormous contributions of the organizers of this conference, Dr. Suresh Chandra, Dr. Chiranjeev Konar, and HOD Physics, Dr. Ashok Kumar, with a very strong team and with their faculty members towards this great job, which has given us a chance to interact with eminent scientists and technocrats and enlighten us with the innovative ideas in astronomy and astrophysics. I wish all the success to this workshop, and I'm sure that this workshop will motivate other physics students also to explore the mysteries of astronomy and astrophysics. Wish you all a very enlightening session. Thank you.
Thank you very much, ma'am. You have always been a constant source of motivation for all of us. In fact, we are fortunate to have you and working under your guidance. So it is an honor as well as pleasure to now invite Dr. W. Silvamurthy, President, ASTIF, AUP Noida. Dr. Silvamurthy has served Defense Research and Development Organization, DRDO, Government of India for 40 years. He is presently member of Scientific Advisory Committee to Cabinet and is a member of High-Powered Committee appointed by ICMR to review 12th Plan Proposal and Chairman of Technology Commercialization Committee of ICMR. He has published more than 250 research papers in journals of repute, including the 18 books. He has been a member of Indian delegation to World Health Assembly under the chairmanship of Health Minister. He has represented our country at the Organization for Prohibition of Chemical Weapons. He has been awarded a number of prestigious awards, including CSIR, National Award for SNT Innovations, presented by Honorable Prime Minister of India. Academician Mr. Mirkov Award for the contribution of high altitude medicines and technology leadership by DRDO 2010. So it is being presented by Defense Minister, and Lifetime Achievement Award from Honorable President of India in the field of clinical and preventive cardiology, and ICMR Shakuntala Amirchand Award, and many more. So I would like to now call Dr. Silvamurthy
Thank
to
you.
enlighten address.
Thank you, Dr. Shafari, for this very kind and generous introduction. Let me also join my colleagues in welcoming our very distinguished speakers, participants, almost 200 participants online on this important workshop on recent advances in astrophysics. Everyone in Indian science knows Meghnad Saha. You know, he's an icon in the field of basic fundamental science, astrophysics, astronomy. In fact, we can call him father of astrophysics and astronomy. Even time, Professor Meghnad Saha started exploring the universe, and he came out with a very, very valuable equation. It's known as Saha equation. And this equation really addressed that what is the temperature, what are the chemical molecules in the stellar region, and how do you identify this, how do you compute this? So all this, he paved the foundation, he laid the foundation. And so today we remember Saha, a very distinguished astrophysicist. And in 1920, as early as 1920, he talked about Saha thermal ionization equation. He has been in the University of Allahabad, Department of Physics, and that is a well-known, very premier university, Allahabad University. And his equation helps to understand the stellar atmosphere, stellar chemistry, the chemical composition over there. So all these are very, very important contributions of Professor Meghnad Saha. Then he also established a very important institute, Calcutta Institute of Nuclear Physics, and he was fellow of Royal Society. So as early as in Britishers' time, he made all these achievements. And also in independent India, he continued to contribute in the field of astrophysics, and he has many, many publications in these areas. So we salute this noble soul who has really paved the foundation for Indian astrophysics and also advanced the knowledge at the global level, the astrophysics, and took India to a global map in this area. Man has always been very inquisitive to understand the nature, the earth, Mother Earth, and also going to space and then going to further up into the stellar, and as well as in the planets and universe. So yeah, the man is always very inquisitive, very curious to understand the creation of God. So in that, this astrophysics, astronomy is very, very important. Everybody gets excited when you talk about the different planets, and also we are looking for life in other planets like the Earth. Do we have other life elsewhere? So all this comes from your study, the astronomy, astrophysics. I'm not an expert in the field, but then I'm also excited to know and hear more about this astronomy, astrophysics. India today, in science and technology, every domain, we are growing up. And with minimal input, we have maximized through our intellectual capital the outcome of these research. Today, we are third in publication, 9th in patents, and also Nature Index, we are number 7, Global Innovation Index, we are 40. So India is growing very fast because we have that in our genes. Vedas, Upanishad, Bhagavad Gita, Yoga, Ayurveda, and even astrophysics, astronomy, even before Saha. And there was, if you look at the ancient literature, you will find the astronomy, astrophysics knowledge available as a base in our the ancient literatures. So this shows in our Indian intellect as well as the intellect of the human being. So that is why in this workshop, I'm sure we will further advance the knowledge in this field, and let it be not a routine taking stock of what we have achieved, but where do we want to move from here? Where do we stand and where do we want to move? How do we move? So let this workshop be a platform to look at a global initiative to look. And finally, I would like to mention the host institution, Amity, Sunita Ratan, in this Amity Institute of Applied Sciences, and Professor Suresh Chandra. And we have a number of our colleagues, Dr. Konar, Dr. Jyoti Katyal, Dr. Shpali, and many other people who are involved in our department, in our Amity Institute of Applied Sciences, who are contributing in the field. They are collaborating. They're all very keen to work with you. All the experts who are there in the screen, and also those who will be joining, like we have Dr. Saikia and Dr. Anand Hota, Dr. Prem Kumar Das, Professor Dipankar Banerjee, Professor Yashwant Gupta, Dr. Vibhuti Parida, Dr. C. Kumar, and many others, many more who will be joining us. So we are all very keen to work because Dr. Ashok Chauhan, the founder president who has created the whole Amity universe today, which is 12 universities in India, 18 campuses abroad, 28 schools. We have 200,000 students, 10,000 faculties, 5,000 PhD scholars. We have published more than 30,000 research papers in journals of repute. Our H index is 108 today. And also we have patents, 1,800 patents filed, and many of them are getting commercialized through translational research. So Amity is really emerging as a research and innovation driven university under the able leadership of the founder president, Dr. Ashok Chauhan, and also the chancellors, Dr. Atul Chauhan, Dr. Sip Chauhan, and also Dr. Mrs. Amita Chauhan. So with this, the final message I want to give is, let us bring synergy. Let us connect with each other because we are aspirants of excellence. But if we really want to make path-breaking research and make an impact at the global level, we have to connect with each other. So this is where the mission synergy, which again Dr. Chauhan has promulgated, that we should connect with people and bring force multiplier effect through synergy of our efforts. So this is one message I like to give. Let us connect with each other and network with each other and bring synergy in our efforts so that we will be able to do things faster and also better. So with this, once again, I welcome each and every one of you and compliment Dr. Suresh Chandra, Dr. Konar, under the leadership of Professor Sunita Ratan for this wonderful initiative to hold this workshop. And my dear students, this is an exciting area because I see many students, almost 200 people are attending. Many of them are students. This is an exciting area. You should you encourage your friends, relatives to come into astronomy, astrophysics, because this is a field which has not been explored. And we want more students, youngsters from India and other countries to come into this field, exciting field to understand, explore, and all the mysteries of creation of the God. Thank you very much. My best wishes. I'll be eagerly looking forward to the outcome of this one-day workshop, which I'm sure will bring out specific, concrete outcome and recommendations for further follow-up. Best wishes. Thank you. Have a wonderful day ahead.
Thank you, Dr. Sulamurthy, for such an enlightening address. And it was an immense pleasure for us that you joined our event. And your precious time was of great importance for us. Your involvement and interest towards our organization is a great support for us. Thank you, sir.
Dr. Shifari, I'm just trying VC's office. So I think she'll be joining in 1 or 2 minutes.
Okay, ma'am.
Yeah, 1 second, I'll just.
Now I would like to hand over the session to my colleague, Dr. Jyoti Katyal. So she will continue the session.
Thank you, Dr. Shefali, ma'am. Just let's wait for 2 minutes for
Thank you. She's just joining. Just there is a small technical problem. Ma'am is trying to join. One or 2 minutes she'll be here. In the meantime, I would like to thank Professor Dhruv Sekya that you're very busy. We all know that still you have come to join this inaugural session and have given your consent to deliver the talk. Even to Professor Anand Hota and Professor Yashwant Gupta. I think that Professor Dipankar Bhattacharya I can see. So we are really thankful, sir, and we really look forward to have you personally, physically here in Amity University, but I think we are all busy, so we have to plan it much in advance so that we book your tickets and so that we can see you in person in Amity Institute of Applied Sciences. I think ma'am has joined. Yeah, so you can start. Jyoti, you can start, please.
Yes, ma'am.
Welcome, ma'am. Thank you so much for joining. Yes, Jyoti.
It's with great honor that I now introduce our VC ma'am, Dr. Balvinder Shukla, person who wears many hats. Not only is she an academician, as a professor of entrepreneurship, leadership, and IT, she has great interest in every field of research, is an excellent administrator. She has a vast number of years of teaching and administrative experience, and has published many research publications. She is strategist, institution builder, and inspiration leader, along with being an avid researcher, teacher, trainer, and business leader. She has received many honors and awards and has contributed a lot towards making MET what it is today. She has been the motivation and guide behind organizing this workshop. And now I would like to invite her to address the session. Over to you, ma'am.
Thank you very much. Very good morning to all the.
Good morning, ma'am.
Very good morning to all the distinguished guests, my colleagues, faculty members, and participants. First of all, I would like to extend a very warm welcome to all the distinguished speakers in the subsequent sessions and participants for this very important one-day workshop on recent progress in astrophysics, a tribute to Professor M.L. Saha, who was a renowned scientist, researcher, and had created many benchmarks in the field. I'm sure that the workshop in astronomy and astrophysics should take place regularly, and because the kind of the developments in this area happening have the direct application in the various fields, and the kind of the technological developments are needed in times to come. Therefore, the knowledge of astronomy and astrophysics in the relevant fields is important, and therefore all the researchers, it's important that all the researchers get together from not only from the from India but from across the globe to understand and know what developments are happening and what are these applications, and so the collaborative research between the researchers of various universities and the research centers can be undertaken, and to build the synergies and to contribute to the technological development and the economic development of the nation. And this workshop, I'm sure that will help to disseminate the knowledge of fundamental science and the difference between astronomy and astrology. And our country, we know that has a very rich history of knowledge in various branches, uh, including the astronomy. And our country is in a great position in astrophysics research. The India has a giant matrix radio telescope built and operated by the NCR at Taifer in Pune, and AstroSat built and operated by ISRO and other institutes. Devasthal Optical Telescope built and operated by ARIS at Nainital, and Himalayan Chandra Telescope in Henley, Ladakh, built and operated by the Indian Institute of Astrophysics, Bangalore. So India has a very, very rich resources. It's only that how these resources can be used by the researchers to make the new discoveries and new innovations. And I was going through the profile of the the participants. I think the school stewards, college stewards, PhD stewards, faculty members in the profile. I think this is the one of the workshop where you get the whole range of the participants. And we see that today the school children are having the immense interest in the technological development and scientific research. And the national education policies are also focusing on that, how the interest or can be inculcated in the school children for the science technology, because the science is the foundation for bringing the many of the innovations. And we have seen in the recent times how the Indian students have been winning the international competitions, even at including at NASA and all. So I'm sure this workshop will not only give an understanding of this field, but it will also create interest amongst school children or the college students towards astronomy and astrophysics, and pursue their career in science and technology. And so as we have the number of telescopes have been installed at the various locations, and I'm sure that to use this astronomy instrumentation for not only for use but to maintain it and to operate it, a lot of technical experts are required. So therefore, the career opportunity point of view, there's a lot of opportunities now for the youth in this field, and student can build great career in this. And as we know that India is involved in various mega projects like a square kilometer array or 30-meter telescope or the laser interferometer gravitational wave observatory, LIGO, and therefore the stewards from the various universities need to understand and know what the career prospects. And this workshop, I'm sure, is going to not only educate the student but also share the what are the career opportunities are for the students, and all those senior academicians and researchers who are present in this workshop. I'm sure that they will work together, collaborate with each other, and may build a long-term collaborative research associations where the faculty and the researchers of various institutions can work together on the projects and bring the new discoveries and the new innovations. With this, I would like to thank Dr. Neeta Ratan and Professor Suresh Chandraji, and who have initiated this workshop. And so, Dr. Chandra, I'm really looking forward what new initiatives you are going to take in this field and how the research collaborations can really be built. So many congratulations to you and to your entire team under the leadership of Dr. Sunita Ratan. I'm sure we will see the good outcome of this workshop. So wish you all the best and great to this workshop. Thank you.
Thank you. Thank you, ma'am.
Thank you so much, ma'am. Thank you for coming.
Thank you very much, ma'am.
During the time.
Yes.
Thank you, ma'am.
Thank you.
Jyoti, you can.
Thank you, ma'am. It's always been a pleasure to hear from you. My heartfelt thanks to you for the constant encouragement, guidance, and providing a stimulating environment for such educational developments. Now, I would like to invite physics and co-chairperson of WPRA 2022 for votes of thanks. Over to you, sir.
Thank you very much, ma'am. Am I audible?
Yes, yes.
Yes, sir,
audible.
you are audible.
A very warm welcome to all you here. Respected Honorable Founder President, sir, Chancellor, sir, Vice Chancellor, ma'am, Dean Science and Technology, and the Head of Institution Applied Sciences, Professor Sunita Ratan, ma'am, Honorable speakers and participants. A very warm welcome to you for this workshop. I'm here to welcome you for this workshop titled Recent Progresses in Astrophysics, a Tribute to Meghnad Saha, organized by the Department of Physics, MIT Institute of Applied Sciences, and MIT Institute of Astrophysics. Our university organizes conferences, workshops, faculty development programs, etc., consistently on various topics. However, in Noida campus, this is the first workshop on astronomy and astrophysics. We are proud to have been able to gather the support to organize this, and we are keenly looking forward to organize workshops in future also. With the implementation of new education policy, this has also become extremely important for our students pursuing career in science and technology related careers. We owe it all to the founder president, sir, Dr. Ashok K. Chauhan, Chancellor, sir, Dr. Atul Chauhan, sir, VC ma'am, Professor Balvinder Shukla, and Head of Institution and Dean of Science, Professor Sunita Ratan, for their encouragement and support. I, on behalf of organizing committee, thank them all. I express my heartfelt gratitude to the speakers and all the participants who have agreed to give their valuable time for this workshop. Finally, I thank the IT department for providing the online platform for which we are virtually meeting here. Thank you very much, and wishing you a great success to the workshop. Thank you very much once again. Over to you, Judy.
Thank you, sir, for your wonderful words. You are always being an inspiration for our department, and we hope that under your guidance, our department will definitely rise to a new height. Now, with all blessings, Dr. Vimli Parinder. Over to you, sir.
Okay, thank you, ma'am. And good morning to all.
Good morning.
So it's my great privilege to chair this morning session of the technical round. So it's also a great pleasure to invite our first speaker of the day, Professor Dhruvajyoti Saikia. So let me introduce him. Professor Saikia is a renowned professor in the field of astronomy and astrophysics of the country. Professor Saikia did his PhD at TIFR Bombay in the year 1985 and was a postdoctoral researcher at the University of Manchester, UK. He was a faculty at TIFR and worked many years, and later on he held many academic and administrative positions, including being a professor at TIFR, dean at the National Center of Radio Astrophysics, and vice chancellor at the Cotton University, Assam. Currently, he is a visiting professor at the IUCAA, Pune, and Professor Saikia has been a visiting professor at many international universities. He has published more than 150 research journals and supervised 12 doctoral students and 7 master's students. He received many national and international awards and served as a member of many important scientific committees in the country. With this brief introduction, let me welcome Professor Saikia for his talk.
Thank you very much. Thank you very much. I'll share my slides.
Over to you, sir.
Okay. The slides are visible, right? And you can hear me?
Yes, sir, we can hear you.
Okay, thank you very much. Firstly, let me say it's a real pleasure and privilege to be able to participate in this workshop on recent progress in astrophysics at Amity University as a tribute to Professor Meghnad Saha. A lot has been said about Meghnad Saha. He's an inspiration to many, and I just wish and hope that many more of the younger generation will read about his life and his contributions. Although Saha's equation was a seminal contribution in our understanding of astrophysics and stellar spectra and the nature of stars, he's also very widely known for the societal contributions which he made. And that is something I think which one should also be aware of. He not only talked about the river management, radio development, power development, etc. And through his journal Science and Culture, which he started, he and his students he took them on flood relief work in Bengal, and was a critic of the government's policies of the time. In fact, when Nehru was scheduled to give a talk at Calcutta University, he actually told them that get away from the old ideas of just spinning and weaving and get into embrace science and technology for amelioration of the state of the masses of India at that time. Considerable progress has been made, but we also know the status of the country today, where millions are without jobs and in abject poverty. So he was also against irrational thinking, against superstition, and he spoke out very strongly and wrote widely on these themes as well. And in this post-truth world where propaganda arrives large in various parts of the world, including here, that his is a life that should be an inspiration to many. So it's a real pleasure for me to see this symposium, this workshop being dedicated to one of India's stalwarts, Meghnad Saha. With these words, let me start my, the first talk of this workshop. And since the audience is very large, I was not sure where to pitch it. So some of it will be elementary and some of it will be hopefully a bit more advanced. So there is something in it for everybody, okay? Now for the youngsters, you know that, that if you actually shone a beam of light or a laser beam to the moon, it would reach there in about 1.3 seconds. And to the sun, the sunlight comes to us in about 8 minutes or so. So if something happened in the sun, you would see it 8 minutes later. That is the time that light would take to travel to us. And you can imagine how far the moon and the sun is from us. Now, this object which I have shown over here, and which would be what I will discuss later in this talk today, is a giant radio galaxy. Okay, giant radio galaxy. And just to give you the immensity of the size of these objects, you can realize that the distance to the sun is covered in about 8 minutes by light. Here, actually, the size is about 6 million light years, which means that light takes about 6 million years, not in seconds or minutes, not in years, but 6 million years to go from end to end. So such an immense objects which pervade our universe. What you see over here in blue is a radio image of the sky, and radio is a wavelength range which our eyes cannot perceive, and so the color is a false color, just to illustrate to you the emission regions from where the emission comes. And this image has been made by the giant meter wave radio telescope, which has been mentioned several times earlier. It is one of the most sensitive radio telescopes operating at low radio frequencies. Radio frequencies range from about a millimeter or so to several tens of meters. You may have to change the ruler many times, but any wavelength which you can measure with a ruler is a radio wave, just as a thumb rule kind of thing. Now, I will come to it a little later, but this radio source, for example, all these radio sources are associated with a parent optical object. And this parent optical object over here, which you can see, is a galaxy. Okay, so this radio image is superimposed on an optical image, which shows the stars of the galaxies. Some of it are nearby stars, some of it are more distant galaxies. This is associated with a fairly distant galaxy. What you can see over here is that there are jets of plasma, highly relativistic plasma, which is squirting out in the form of jets at highly relativistic speeds, initially very close to the speed of light in opposite directions. We shall try to understand a little bit of how that happens in the latter part of the talk today. These kinds of galaxies which spew out these relativistic jets, which are highly energetic and emit copiously at radio frequencies, are referred to as active galactic nuclei, and such galaxies which harbor these active galactic nuclei are known as active galaxies. Okay, but before I go in a bit more into these sources, I should probably take a step backward and just talk to you about galaxies, because many of you are young, many of you are students and may not be exposed much. So instead of getting too technical, I shall try and cover a little bit of elementary stuff as well. Galaxies, as you know, are gravitationally bound systems consisting of stars, okay, millions to billions of stars, depending upon how large the galaxy is. The medium between the stars, which is full of gas of all kinds of temperatures and densities, referred to as the interstellar medium, the medium between the stars. And all massive galaxies host a supermassive black hole in the center of these galaxies. And when I say supermassive, I mean about 10 to the power of 6, that means about 1 million solar masses to billions of solar masses. Our galaxy too has a supermassive black hole, as we shall see in a short while. And all this matter which you can see, the interstellar medium, the stars, and you can see the effects of the black hole, but not directly the black hole itself, is embedded in a halo of dark matter. Why dark? Because we cannot see it, we cannot detect it. But how do we know it is there? It is because of the gravitational influence of that matter. Okay, we shall look at this in a little bit more detail later. Galaxies come in different shapes and sizes, and they vary in mass and size as well. Now, Edwin Hubble was one of the early ones to classify galaxies. Galaxies come in all shapes and sizes, as I said, and he considered those as they appear in the sky to us. And his classification was based largely on relatively nearby galaxies, which he could observe in great detail with the telescope which he was using. So you can see galaxies come as elliptical galaxies. They look like an ellipse. It could be an egg-shaped projected onto the sky, or it could be a bun-shaped, which are prolate and oblate shapes, or they may have spiral arms and have a spiral structure, as you can see the ones on the right. Some spiral galaxies have a bar, so they're called barred spirals, and some do not. And he classified these galaxies in this form, which is often referred to as a tuning fork, just from the shape, the way it is classified. Hubble thought they may evolve from one end to the other, but today we know that that is not correct. And the evolution of galaxies itself is one of the frontier areas of astrophysics, how they form, how they evolve as time goes on. But Hubble's classification was based on the relatively nearby universe, where the galaxies which he could observe well with his telescope. These are just images of real galaxies. The left ones are from the ground-based telescopes, and the right ones are from the Hubble Space Telescope, where you can see greater detail because the resolution is better. It is often more sensitive as well. And there are galaxies in between, which are called lenticulars, but we'll not get into too much of detail in today's short presentation. Is this all there is to it in the world of galaxies? The answer is no. The universe is indeed extremely rich beyond what Hubble had classified. I'm just giving you a few examples over here. The galaxies which don't fit into any of these patterns of ellipticals or spirals, they have very complex shapes, and these are irregular galaxies which don't fit into this pattern at all. Then there are galaxies which are extremely dim, which could only be brought out by high dynamic range and very sensitive observations. And you can see little fuzzes over here in between, which are known as the low surface brightness galaxies. And these more and more of these galaxies are being cataloged as observations get more and more sensitive. You can see this one and this one here. And on the leftmost panel, what you see are dwarf galaxies. For example, our galaxy, the Milky Way, is about 10 to the power of 11 solar masses or so, slightly over that. But these are much smaller in size. They have far fewer stars, maybe 10 to the power of 7, maybe 1,000 or more than that times lower. And these are referred to as dwarf galaxies. And the dwarf galaxies in number are much larger. Galaxies also don't occur in isolation. They often occur in groups and clusters. Our galaxy, too, the Milky Way, is part of the local group of galaxies. And the local group of galaxies, in terms of sheer numbers, is dominated by the dwarf galaxies. They outnumber them. And studies of these are extremely important to understand how our structures formed, how our galaxies formed, right from the early times when the universe itself formed and started evolving. As I mentioned, galaxies don't occur in isolation. They occur in groups and clusters. They move about. And often when they move about, they interact with one another by their gravitational influence. They not only interact with one another, they can collide with one another. They can go through one another. A bigger galaxy may swallow up smaller ones, and you may find smaller galaxies in the core of the bigger galaxies, as though you have surprised a massive galaxy in having its dinner. So half of all massive galaxies undergo such mergers. So what we see today in the universe, in the nearby universe, is a result of the evolution of the galaxy over time, where it may have interacted, whether it may have merged, and all these events have profound effect on the evolution of galaxies. It affects star formation, it affects formation of the active galactic nuclei, which I referred to earlier. And these are aspects which affect the evolution of galaxies. The jets themselves can alter the interstellar medium, can affect it later, as we shall see, we'll discuss a little while later as well. So are galaxies the same everywhere? That is another question that we can ask. Are the shapes the same when we go further away? And how common are the massive ellipticals or the spirals? This is a graph. I'll use very little equations and just one or two graphs. This shows the stellar mass of the galaxy. Okay, this is in log scale, so this is 10 to the power of 12. This is 10 to the power of 11, and it accordingly goes down. So it increases from right to left, and this is the fraction in a large sample of galaxies. So you can generally see that the ellipticals are the more massive ones, whereas when you go to the low mass ones, the irregulars dominate, and in the middle you find that the spirals dominate. And there have been suggestions that at least one way of forming elliptical galaxies is by the merger of spiral galaxies. Simulations as well as observations seem to support this scenario. It is definitely part of the story, but whether it is the entire story, we do not quite know. These are images of high redshift galaxies. When I pose the question, do galaxies look the same everywhere? The answer is not necessarily. You'll get spirals and ellipticals in large redshifts as well, but you find far more galaxies which are very complex in shape. Because early in the universe, the galaxies were interacting far more than they do in the nearby universe. These are optical images of galaxies, some of which are also strong radio sources and some not. Okay. Now, this is an image of the Hubble ultra deep field. Okay, and what you see over here are literally thousands and thousands of galaxies. They're nearly 10,000 galaxies over here. They looked at a region of the sky where there is very little stars or no stars. There is one over here you can see, but so that you can see deep into the universe and look at the populations of galaxies. And the smallest, the reddest galaxies are among the most distant existing when the universe was just about 800 million years old. Now the James Webb Space Telescope, or the JWST, is pushing that even further and detecting galaxies almost at the time when galaxies were first forming. I've just posed a question over here, which you can think about and we can discuss in the chat, or later I've given my email address as well. You can sort of email me if you have a question as well. Why can't we see so deep with our eyes? I'm not going to address it, but I would like students particularly to think about it. I'm showing you optical images of galaxies. And I've told you that the medium between the stars is occupied by gas. But the gaseous component can often extend far beyond the optical galaxy. Such is the beauty of our universe. Here, what I've shown you is an optical image, which you can see in white. These are some background stars. And the blue fluffy lot which you see is just gas of neutral atomic hydrogen. Okay, the neutral atomic hydrogen is something for students of physics where the electron is in the ground state. The gas is cold, it could be about 100 degrees Kelvin. There's nothing to excite it to the higher energy level. And the only way you can detect it is by what is called a spin flip transition, when the electron and proton spins are aligned parallel and anti-parallel. And that wavelength is about 21 centimeters. And because it is a line, you can go and detect, not only detect a line, but also detect its motion. So once you detect the motion, you can go and study the dynamics of the galaxy and see how the gas is moving. If it was just continuum emission, you would not be able to do that. So you can see that there are galaxies where the gaseous component can extend many, many, many times larger than the optical galaxy. So if you had just an optical view of the universe, you'd be poorer in our understanding of the universe. You need information at all kinds of wavelengths, and radio astronomy has played a very, very important role. Similar objects have also been discovered with the Giant Meter Wave Radio Telescope. This particular image has been imaged with the Westerbork telescope and by Raffaele Morganti. Now, when we monitor the dynamics, then we can look at how the gas is moving. On the left, what I've shown over here is how the planets move with what velocity around the sun. You know that the Earth moves around the sun at about 30 kilometers per second. It's a pretty large speed. 30 looks very small, but this per second. So you multiply it by 3,600 and you'll get kilometers per hour, and it's a huge number. So but you can see that it is going down systematically. And that is going down systematically as per Kepler's laws of motion. Almost all the mass is concentrated in the sun over here. But using neutral atomic hydrogen, if I look at the motion of gas in galaxies, then I find that it is not coming down. It will not come down exactly as this because all the mass is not concentrated in one point like the sun. But even if you calculate from the distribution of stars, it should start coming down. But it doesn't. And the only way to understand it is that there is matter over there which we cannot see. And that matter is what is referred to, what I mentioned earlier, as dark matter, a term which was invented or suggested by Zwicky when he looked at clusters of galaxies, and which has been studied extensively by astronomers over the decades. And it forms a fundamental unit of galaxies. All galaxies, or almost all galaxies, have dark matter associated with it. This is an image of our galaxy, the Milky Way as you would see it from the Earth. This is taken from a site in Chile. What you see at the bottom over here is a nearby town, the city lights coming in. But what you see is an arch, because our galaxy has a disk kind of structure. And this is the way you would see it when viewed from the sky. This laser pointer points at what is the center of the galaxy. And all these dark patches are because of absorption of starlight by the interstellar medium of the galaxy. When you look at the night sky, the sky looks pretty studded with stars, particularly if you're in a small town where city lights don't interfere and the sky is dark, you'll see thousands of stars. But But when you look at what fraction of volume the stars occupy, the number is very small. Just to give you an idea, I put the volume of the sun and the volume till the nearest star, Proxima Centauri. The volume of the sun is about 700,000 kilometers. Distance to Proxima Centauri is about 10 to the power of 13 kilometers. So the fraction of volume occupied by the sun that is our galaxy neighborhood is about 5 times into 10 to the power of minus 24. If you want to get a physical idea of what that means, you take a distance of 100 kilometers, that's about 10 to the power of 8 millimeters, cube it to get the volume, that's 10 to the power of 24. So it's like a grain of sand and the next grain of sand is about 100 kilometers away. So if you're sitting in Noida, then it's probably, Sonipat or Bagpat or Rohtak away. If you're in Bombay, it's probably somewhere between Pune and Lonavala is your next little star, which will be the size of a small pebble or so. So the space is largely empty of stars, but it's not empty of matter. It contains the matter between the stars, which is referred to as interstellar medium. Today time is short, so I didn't put in pictures of the interstellar medium as well, but you can see beautiful pictures of the pillars of creation, one of the first images, early images made by the JWST, which is just coming into the media. This is what our galaxy looks like. If you want to reconstruct the picture, this is the disk of the galaxy, this is the bulge. We are in a very nondescript part of the universe, about 28,000 light years away from the center. And this whole, everything that we can see is over here, the visible or luminous part of it. There's some halo stars, and we are embedded in this whole dark matter halo. How far does the dark matter halo extend? Definitely much, much beyond what we can see, but how far we are still not sure. But it is well beyond. The last item that makes up our galaxy are the supermassive black holes. And this is an image of motions of stars which are monitored to infer the mass of the central supermassive black hole. So we have a supermassive black hole center sitting in the center of our own galaxy, about 4 million solar masses or so. And this mass was measured, estimated by applying Kepler's laws of motion effectively. General relativistic corrections will have to come in when a star goes very close to the black hole. S02, you can see over here, goes very close to the black hole. And definitely it's not a massive cluster, because SO2 would not have been able to get so close, it would have interacted with it. So these are the primary constituents of it. Andrea Ghez and Reinhard Genzel were the two which measured the motions of the stars. Very high resolution, very advanced technology is required, and it's years of monitoring, decades of monitoring that has led to the estimation of the mass of this galaxy, for which they were awarded Nobel Prize. This is just shows a 3-dimensional animation of what I showed you just a little while earlier in 2 dimensions. So the last 5 or 7, 10 minutes, I will just spend on looking at the radio galaxies and how did it come about. So for thousands of years, man was confined to looking at the universe in the optical region of the spectrum. Initially with the eyes, then with photographic films, then with charge-coupled devices, etc. Okay, and the fact that the celestial universe emits at all kinds of wavelengths started off with opening up the radio window due to the pioneering efforts of Carl Jansky, who discovered radio emission from the center of our galaxy and reported his results in early 1930s, 1933 to be precise. Now with radio emission, you can make an image of the sky. This is a relatively low resolution image, 12 arc minutes or so. To give you an idea of what that means, the angular resolution of the human eye is about an arc minute. So if something subtends an angle about an arc minute, you should be able to distinguish the structure of that object and separate 2 objects which are separated by an arc minute. These peaks of emission are radio sources. They're radio emission in the sky. The little background ripples are the noise over there. Now, if you just saw a radio emission, you'd never be able to say what it is associated with or what is it coming from. Is it very close by? Is it far away? So to be able to do that, you need to make good radio images of high resolution as well, and also look at it with comparative images at other wavelengths. Here, a radio image with a high resolution of about 45 arc seconds, which is similar to the resolution of the human eye. And so the radio image has been superposed on the optical image. Now you can see the optical images. These are galaxies with which these radio sources are associated. Sometimes there's more than one galaxy, so you need higher quality or high resolution images to be able to say which one is associated. To fast forward a bit, when you make high resolution images and superpose them on optical images, what you found was completely unexpected and stunning. And that is examples of the first image which I showed you, that there are huge plumes of radio emission squirting out from the nucleus of a galaxy via relativistic jets. And these are two examples. This is Cygnus A and this is Hercules A. These were some of the early galaxies which were identified. And today we know literally hundreds of thousands of them. But they still continue to pose challenges in terms of the theoretical understanding of how such energy is generated and transported over such large distances. This gives you a scale of Cygnus A, which I showed you, which is 120 kiloparsec. I didn't introduce the term parsec. Just remember that parsec is about 3 light years. So you multiply by 3 to get it into light years, okay? These are amongst the 2 largest sources. They're very similar in size. They have measured it from the edges, so they've got a slightly larger number than this, but they're very similar. This was one which we had discovered with the GMRT and using the Effelsberg telescope and the Very Large Array in New Mexico as well. But you can see how puny, how small this one is. And there are even smaller ones, just less than about tens of light years across. So those are the baby galaxies, and they grow larger and larger with time. Now, what leads to the formation of the giant sources? Are the jets more powerful? Do these occur in low density environments so the jets are about to go out more easily? Or is it because activity keeps recurring? How do they end their lives? So these are still questions which we work on and try to probe. In these studies, actually, Dr. Chiranjeev Konar and Dr. Anand Hota, who will speak after me, have also made significant contributions. And I will just share some of these results and pose and discuss a little bit about how the energy is generated. This is a galaxy which Chiranjeev Konar made the image and a significant contribution, shows that when the energy is switched off, for example, you don't see the jets, you see plumes of emission, which will also slowly decay with time. And these electrons will radiate via a process where they're moving at ultra-relativistic velocities in the magnetic field, giving rise to what is called synchrotron emission. The higher energy electrons lose energy faster. So you can see the emission at higher energies will go down with time, and depending on how rapidly, how far down this break or in the slope goes, you can estimate the ages of these objects. So for this one, we had estimated about 150 million years. Because there is a nucleus, there may be some evidence that it is going to restart, but you can see that there is a dip in the center rather than a peak over here, suggesting that this is indeed a very old radio galaxy. This is another image which Chiranjeev.
Sorry to disturb. So, sir, you have 5 minutes left.
I'll finish in 5 minutes.
Yeah, then we'll have question answer.
Okay. The galaxy is not shown here. And these are examples of sources where the nuclear galaxy, for whatever reason, can start re-emitting again. Okay, and these show evidence of recurrent activity, which is another sort of interesting area of research. We still do not know why exactly it restarts. Possibility ranges from availability of new fuel, which is a distinct possibility, but the observational evidence to distinctly pinpoint it is rather thin at the moment. So as I mentioned earlier, you can go and estimate ages from the way the spectra is steep. For the young ones, which is the inner one over here, you don't see steepening, whereas for the older ones, because the electrons are very old and the high energy electrons have lost energy, that you can see a steepening in the spectrum. So these are the techniques which are used to measure ages of these objects. And this is a very interesting object, which Dr. Hota, who is going to speak after me, discovered. And here you can see not only 2 cycles of activity, but actually 3 cycles of activity. This is just one of 2 such examples known. And the other interesting thing about this object is that it is associated with a spiral galaxy, whereas generally all these jet sources tend to be associated with radio galaxies. So I'll spend a few minutes just telling you how this energy is generated, and then we'll close it for discussions or questions. The luminosity is very large. You can see it's about 10 to the power of 41 to 46. Compare it with the sun, it's about 10 to the power of 33 ergs per second. This is orders and orders of magnitude larger. The total energy is about 10 to the power of 60 ergs or so. So if you calculate how much energy the sun will emit in all its lifetime, is 5 billion years old now, it'll live for another 5 billion years, factor all that in, this energy would still be orders and orders of magnitude larger than that. What is the source of this energy? Is the question that one asks. I will try to address that in a few minutes, and then we will close. I've shown a picture of this bearded vulture called Lammergeier, and what its diet consists entirely of bones, and it uses gravity. It will take the bone to a great height, drop it, it breaks to pieces, and then chew on the bones. So animals have learned to use gravity, the source of gravity, as a source of energy. In fact, the naturalist and Pliny the Elder in Roman times spoke about tortoises being dropped from a height to crack open the shells. And it is really nearly 2,000 years later that zoologists actually observed this when they saw golden eagles soaring and dropping turtles from the sky to get to the insides and breaking the outer covering. And often multiple drops are required. You see similar things in seagulls breaking shells, crows, breaking sort of nuts. They also let cars crush it. You can watch some of this video when Dr. Konar shares the slides with you. So gravity is something which the animal world had learned to use much before, from very, very early on, much before us. And it is really gravity which is governing the origin of this energy. When matter falls from a great height, the potential energy becomes more and more negative. The kinetic energy builds up. And when the kinetic energy hits the surface, it is generated into heat. So if I express this without getting into the mathematical details as a rate at which mass falls multiplied by c squared, and this is a factor which I call the efficiency. Xi is what is known as Rg, which is a term, don't worry about the jargon, it's called a Schwarzschild radius, which essentially depends on the mass of the object, and R is the radius of the object. Now you can see over here that when you go to a neutron star, which is a remnant of a massive star, a white dwarf, which would be the remnant of a star like our sun, you can see the more compact the object is, for a similar mass, the efficiency goes up. When you talk about a black hole, particularly a rotating black hole, you can see it is the most efficient way of actually extracting energy from an object. And that is the viable process for generating these large quantities of energy, not nuclear reactions. Nuclear reactions are far, far less efficient than extracting energy from a black hole. So I'll leave you with this last slide, which basically sums up what I've tried to convey to you, that of an active galactic nucleus and a giant radio source. It consists of a supermassive black hole, which forms an disk around it. The accretion disk is due to matter which is falling into it. A disk forms because the matter comes with a certain angular momentum. And we also have observational evidence of a torus around it. Torus in the nuclear regions, which is like a donut if you're in the US, or a medulla if you're in India. There's a hole in the middle which directs the photons which are coming out. And material within, close to the black hole, which is emitting emission lines, will move at much higher velocities. So these have much broader lines due to the Doppler shifts. And as you go further away, you get narrower lines. So this is the canonical model of an active galactic nucleus. On the upper side are the objects which we talked about today, the radio galaxies, and radio galaxies, the active galactic nuclei. On the bottom side of this panel are also active galactic nuclei, but they don't manage to spew out the powerful jets which we saw today. The reason, we don't quite know. This is something which is still, it's still something one is trying to get very affirmative answers, although there are very interesting ideas floating around in the literature. So I'll leave you with this slide and would be happy to take any questions. Thank you very much.
Thank you very much, Professor Saikia, for this very interesting, enlightening talk. So we have a few questions in the chat box. So it will be very difficult to read all, but I will take some cracking ones. So one question from Vibhu Prasad Misra. So he asks, why we cannot see so deep with naked eye? So our eyes only detect wavelength of visible region, but the light or signal coming from distant galaxies get elongated due to redshift that is longer than the visible range. So we cannot see them with the naked eyes. So probably you want to ask or you want to?
Okay, I will elaborate. I wanted actually the audience to think a little bit about that, but she's asked a question. I will elaborate a little bit on that. There are various reasons. One is of course, the first thing that comes to your mind is the size of the eye, right? Because the bigger the telescope is, the bigger the mirror is, the bigger the collected is, the more photons that you can collect. So one is just the size of your eye, the lens. But even if your eye was as big as a telescope, I showed you the Hubble Deep Field taken with the Hubble Space Telescope, where the reflecting mirror is about 2.4 meters. Now let's imagine a situation where the eye is 2.4 meters. Will you be able to see as deep? The answer is no. Why no? There are two things. If you think about the eye, what you're recording is refreshed literally in milliseconds or so, many times a second, many times a second. Okay, and I mean, if it didn't happen, for example, when Kohli hits a shot, you'll not be able to follow the ball, right? Because your eye, in a telescope, you can integrate for a long period of time. Okay, you can keep looking at the same image and keep adding up the light, but your eye actually refreshes the screen very rapidly. The third is the efficiency of the detector itself. For example, today, the kind of detectors which you use, the charge-coupled devices, that they're approaching efficiencies close to 100%. I mean, 90% plus is quite routine in the efficiency of the charge-coupled devices. Whereas the efficiency of converting the photons that fall in your retina into electrical signals for your brain to interpret is only a few percent. So all these, I mean, these are factors which actually play a role in the eye not being able to see very deep. The size, the quantum efficiency of the detectors, and the ability to integrate. In fact, the Hubble Deep Field was integrated over many months in that area as the telescope, which is in orbit, kept going round and round. Okay, does this satisfy you?
Yeah, I think it is clear to him.
Okay.
So I'll go another quick question. So from Himanshu Kumar. So his question is that, did Milky Way start as a radio galaxy?
Milky Way, actually, the thing is that the Milky Way is a spiral galaxy, and there is no evidence of a jet in the center. But in these galaxies also, which have a supermassive black hole in the center, there could be activity in the center due to the black hole, but we do not know of any sort of collimated jets, which I showed you, going over large distances in our galaxy. But there is evidence of bipolar ejection from the center of our galaxy. For example, at very high energies, the Fermi telescope, which is a high energy telescope, has detected bubbles of emission called the Fermi bubbles. And these are emissions of very high energy photons, which are emitting at X-rays and gamma ray wavelengths, which we detect. So there is activity even in a mildly active galaxy like the Milky Way, but it is not the kind of radio galaxy which we see. So our galaxy has never been a radio galaxy, and there is no evidence even today of the kind of jets which you see in radio galaxies in our Milky Way, but there is evidence of energetic bipolar outflow at high energies, and the Fermi bubbles is an example. There's also X-ray emission, which is there.
Okay, sir. Thank you, sir, very much for your answer. So there are so many questions from audience. It's very difficult to read all these out, but we'll be definitely happy to share with Professor Saikia later. So
Sure.
Yeah, so I just want to thank Professor Saikia. This is a wonderful thing that you have come and delivered your talk, and happy to see you. Hopefully in future, personally, we will meet you, Sykes.
No, thank you, Chiranjeev.
It's a wonderful talk for the which can cater to all kind of expertise, starting from student to the experts.
Okay, thanks very much. I will share the PDF file with you.
Yeah, please send me the email.
And my email addresses are there. So if students or participants have questions,
questions.
I'll try to answer them.
Okay. Yeah.
Okay, thank you very much.
So let us go over to the next speaker. So Vibhuti, please carry on. Yeah. So that will be very great. So
Thank you
I
very
also.
much, Professor Saikia.
Thank you very much, Professor Surya. It is a pleasure participating.
Thank you very much.
Thank both you and Chiranjeev for the invitation. Thanks a lot.
Thank you, sir. So with this, let us welcome to the next speaker of the day. So Dr. R.K. Choube will introduce the next speaker. Over to you, Dr. Choube.
Thank you, Dr. Parida. Good morning to one and all. Good morning, sir. It's a great pleasure for me to introduce our next speaker, who is also my friend, Dr. Ananda Hota. Dr. Ananda is currently working at the Center for Excellence in Basic Sciences, University of Mumbai campus. He received his PhD degree in physics in 2007 from Joint Astronomy Program of the Indian Institute of Science, ISC Bangalore, and National Center for Radio Astrophysics of the Tata Institute of Fundamental Research, TIFR Pune. Then he went for postdoctoral research at Academia Sinica Institute of Astronomy and Astrophysics, Taiwan, and worked there for 5 years. In 2014, Dr. Ananda joined UMDAE CEBS, where currently he is working. He has published a number of research papers in various prestigious international journals and delivered several invited lectures in national, international conferences. He is the member of several prestigious societies, including International Astronomical Union, Astronomical Society of India, etc., and a recipient of several awards, honors, and fellowships. He is also the member of the Principal Scientific Advisors Consultative Group to advise the Government of India on various matters of policy relating to science and society. He is well known in the astronomy community for his news-making discoveries and especially as a pioneer of citizen science research in Indian astronomy. His initiative, Read at the Rate Home Astronomy Collaboratory, is not only the first in India, but is still the only such platform which uses the data from Indian telescopes since 2013. Actually, Read at the Rate Home is a citizen science initiative in which students as well as any professional can learn and do science accordingly. So four of his astronomical discoveries have been press released internationally, creating large public interest in astronomy and bringing pride to Indian science. The title of his today's talk is Black Hole Galaxy Coevolution Study with GMRT Telescope and Read at the Rate Home Citizen Science. With these words, over to you, Dr. Ananda.
Yeah, we are extremely happy, Ananda, to have you here. Please, stage is yours.
Thank you, Dr. Choube. Thank you, Chiranjeev. Thank you, MIT University, for inviting me. It's also a great pleasure that in the introduction program, you mentioned about our discoveries with Dr. Konar. I'm happy that you have noticed this thing. What is actually it is not just a astronomical discovery that gets published internationally. It's also a result of student participation, citizens participation. That is why it deserves larger public attention, and that public attention is not for name and fame, but real work. Okay, I will share my screen and get on to my talk where I can describe it properly.
So Ananda, you have 30 minutes time.
Yes.
And 5 minutes discussion.
Yes. Can you see my screen? Somebody confirm?
Yes.
And you can see the slide changing?
Yes. We can see.
So great. Title of my talk is Black Hole Galaxy Coevolution Study with GMRT Telescope. You have already heard this. And Rate Home Citizen Science. What is this? I will be explaining. So at the left hand, you can see a pretty picture of some galaxy 1, galaxy number 2, and the radio emission from this galaxy because of gas falling into black hole is ejected. That is what is made the news recently. It was press released by Royal Astronomical Society, NCRA, Radatom, CEBS, etc. And on right side, you see a picture of one of the discs of GMT radio telescope. This disc itself is 45 meters, and there are 30 of them spread over 25 kilometers. And what is the other thing? The map of India, where you see various locations, Radatom logo is placed. What is that? That is the trained citizen scientists of Radatom collaboration who are given serious training on how to make discoveries of such exotic black hole galaxy system, primarily using data from GMRT and also using other telescope, of course. And what are these logos? These logos are the institutions who have been supporting this program. Like currently, MIT is welcoming to give a talk and let people know what is this. So I am a UGC faculty at Center for Excellence in Basic Sciences, head of this Radatom Collaboratory. That's how the logos are coming here. A member of IAU, SCA India Consortium. You heard this. Like MIT, Chiranjeev is also representing there. ASI, Astronomical Society of India. IAU, International Astronomical Union, more than 100-year-old organization of professional astronomers. They are supporting how this Radatom-like citizen science collaboration can spread to other countries. So, in one slide, I should never forget people who have invited you to give a talk. Thank you, MIT. So, at the very beginning, I will give you a broad overview of what message you will be getting. As I have been describing, we published this paper in MRS letter. This is the image of that. And I have given the acknowledgement for the funding me, given press release, and some Nature Index, Times of India, etc., the news channels, news media who have connected society with the science discovery. Because primarily the citizen science is connecting people, science and society. So the message is Radatom discovery is named RAD12, that galaxy is named. RAD12 black hole discovery in worldwide is new discovery. That is not the point to note. Point to note is your organizer Chiranjeev and me both are part of it. How you, like students, can be part of such a discovery, I will be giving you the pathways. By joining Radatom exactly. Once you join that, we, Chiranjeev, me, will be training you how to make use of GMRT's freely available data. Once you make the initial discovery, begin with GMRT or other telescope and make your preliminary discovery reports published as a journal. Okay. So, just as a glimpse, I will show you the simulation of that. What exactly is that? This is artist simulation based on our understanding of RAD12, exactly this paper. This is a galaxy elliptical image. This is also a galaxy. I'm going to start the simulation. The galaxies are actually about to merge. They are going around each other, common center of mass at the here. They will be going around just like the two stars, when a star should be going around. One is bigger in mass, light, etc. Other one is slightly smaller, but both of them are elliptical. During this process, at some point, a jet shoots out of one galaxy, radio plasma emitting jet. That jet is visible only in the radio band, and everything yellow that you see is starlight. The pink that you see is radio synchrotron radiation. The stars are giving black body radiation, thermal radiation, just like our sun. And this plasma is not seen anywhere else. There is no atom, no molecule, no gas, no solid, nothing. It is purely electrons, positrons, and protons. Electron definitely sure. They are moving at relativistic speed, close the speed of light, 10% speed of light roughly. And they are gyrating in the magnetic field lines that is there and giving synchrotron radiation. That is being detected by GMRT. So what GMRT detects, I am showing you in pink, as in the picture as well. So this jet comes out there, hits the other galaxy, and suddenly it bounces backward, forming a bubble-like thing. That is what is puzzling, is that in all galaxies, like Professor Saikia described, the jet comes out in both the directions. But in this particular case, the other direction is not seen, even though we have tried to detect it with sensitive observations. And that ghost doesn't pass through. It gets reflected. That is also puzzling. In other cases, when it hits the galaxy, it is supposed to form new stars. That is also not seen. So how this kind of jet and galaxy interacts, it's an opportunity to understand many bizarre things are happening here. That's why public interest and the press release and the letter paper, everything has happened. So this is just the artist simulation, but close to our understanding what is happening. So today, with this kind of 30-minute talk, I will explain what are galaxies, what you can see the picture, what to interpret in the picture when you join as a student, how the student's finding goes ahead and get observed with the GMRT. These things we'll understand in this short talk. Okay, let me go to my slides. This is the context. What is the context? That we are learning as students in universities, in colleges. But we are all equipped with small telescope, small microscope like thing. These are like not research class in astronomical facility wise certainly. This telescope is a toy telescope to understand the concept. What we want is actually GMRT like telescope. So they are research telescope, research facilities. Our science is always high class. We want to image something like first image of black hole. How do you do that? With this facility, you cannot do research. But your aim is bigger. Only then your paper can be published. So this is what is the middle part. That you join a collaboration as a teacher or as a student, whatever, and be part of the data analysis from a big telescope and connect with the concept that you are learning in the college. If the college support it, fine. If the college doesn't support it, doesn't matter. There is something called citizen science. That you stay at home, learn from wherever the institutes are giving the facility to teach you, and join the collaboration and do research from home, however small the amount can be. So there is the modern landscape of outreach, education, and research kind of merged. That is what is citizen science. We have actually two big telescopes. You have already heard. This is GMRT, and on the right hand side is GMRT, and left hand side is Astrosat, India's multi-wavelength telescope, first space observatory. So if some way we use this data, our quality of the paper is automatically reaches high. It is not constrained by the toy telescope, but it is empowered by the big telescope's data. You don't own the telescope, but you use the data. You can own the data. Once you discover the concept, the discovery is your own. So you are empowered by the power of analyzing the data. This is what is the bigger context. What is the bigger context? From a science current science article, that 1930 to today, the way science has been happening in our country is changing its gear, changing its mode. For example, like Professor Saha, Bose, Raman, these are individual excellencies. The laboratory facilities were not that big that they made name. It is the brilliance of their mind only. Then the mode came self-reliance, technology denial, IP generation. Today we are at a phase that we have to be globally competitive. Science paper publication is always a global competition. So how do you become competitive? Realizing your competitive edge in the global science. So aim is always faster, sustainable, inclusive globe. We want always a scalable education plus research model and make use of this kind of large facility. Give me example of Astrosat. This is Astrosat. Another, it has a UV ultraviolet imaging telescope. Another, NASA's ultraviolet imaging telescope is Galax. This ultraviolet telescopes image of a star forming region that we have studied. If we do the same thing from Astrosat, see the quality difference. This 5 arcsecond, this 1 or 2 arcsecond resolution. So when you can see so much of detail, you can do wonderful discovery. Somebody's mic is on, you may mute for the moment. So people from all over India and all over world, US, Italy, Canada, etc. Everybody is trying to use GMRT and Astrosat, etc. because they are world-class facilities, best in the world of its class. So we published a paper, how to understand basically the surface ultraviolet view of star formation in extreme environment in the nearest jellyfish galaxy IC341. Because we're co-author here. This is how with the Astrosat, we have looked at this star formation, highest resolution picture of the star formation, where the galaxy is moving towards the right and top corner, and the gas gets stripped from there and star formation happens in this tail. Some other time we will discuss this kind of star formation study. Here comes Professor Saiki also showed this picture. Chiranjeev and me, our discovery of this exotic galaxy spiral host episodic radio galaxy SPECA, we named it in 2011. This was again in MLS letter news, created a lot of news. And that's how we realized that people are loving astronomy, and why not use people's power to make more discoveries. So I will describe this concept little later on. So when this was probably the first news-making discovery from Indian GMRT. What is the use? This is what is the eye-opener, that when people are loving it, you have the power in your hand. Why not distribute and empower people, and why not make more discoveries? That's how the father of Indian radio astronomy, Professor Govind Swarup, he passed away recently. He is brain behind UT Radio Telescope and GMRT both. He appreciated our effort. How does it appreciate? It was not part of the paper, but he appreciated it. Govind Swarup of NCRT-FR, who is not part of the team, described this SPECA discovery, this finding, as an outstanding discovery that is very important for cluster formation models and highlight the importance of sensitive observations at meter wavelength, long wavelengths in radio observation, provided by the GMRT. So when it's encouraging like this, I kept on asking, what is our global competitive edge that we can publish more discoveries? This is what actually, when I realized, I started thinking of leaving my postdoctoral position and coming back to India. What is India's competitive edge? This is apart from Astrosat, GMRT. Those days Astrosat did not exist, was not launched then. GMRT was certainly there. Largest pool of science and technology manpower, largest number of mobile phone or computer connected to internet, communicating in English, largest pool of IT companies, engineers. So can we combine this man and machine system, GMRT data, if we can combine in some possible way, socio-scientific way, then we can do wonderful discoveries and help the people who are interested in pursuing academic life, their career. So astronomy and development can be together happening. So GMRT has looked at all part of the sky in one single frequency, 150 megahertz or 2 meter wavelength, called PGSS survey, TFR GMRT sky survey. So if you look at any part of the sky, 90% of the sky, it has looked at and created an image. Now, so our job is to train people how to look at that part of the sky, how to spot whether there is a normal white looking stone or there is a diamond. What I mean, whether there is a normal radio source or some abnormal radio source that is potentially important as a discovery. So combining this and this, here comes the radiation. That was the result. That when 2013 we launched it, that time initial members were, Chiranjeev was also initially supporting, like this SPECA discovery. He also realized this is where we should go. What do you mean? That let's combine the man, nationwide, inter-university, any university they may belong to, and the machine, which is our competitive edge, Indian competitive, largest in the world of this kind of a telescope. You all have paid to build this, to run this. Let's take help from all the institutes who are interested in supporting this endeavor. Everybody came forward. It was launched as a zero-funded, zero-infrastructure, Facebook, Google system only. Nothing happens. It doesn't exist anywhere. It exists in the virtual world only. But real benefit everybody is getting because the institutions have come forward to give, because the scientists have come forward to train, because thousands of students have come to learn, because they are making publications, they are getting recommendations, they are getting development in their field. From zero fund, it has helped in people to grow in academic as well as in personal life. So, in summary, this is Reddit-Home. Reddit-Home has a nice website where you can find things in the systematically arranged way. It has a Facebook group for social media continuous activity. 24/7 people are discussing, commenting, uploading photographs, and learning by this kind of discussion. It arranges discovery camps at XYZ means different institute name, the logos that you saw. It may be Institute of Physics in Bhubaneswar, it may be ICTS in Bangalore, it may be HRI in Allahabad, it may be Nehru Planetarium in Delhi. It can tomorrow become MIT University. It runs a program from those workshops, whatever students discover, that preliminary discoveries are followed up for advanced investigation with the GMRT through a program called GMRT Observation of Objects discovered by from astronomy collaboration. How it happens? Because the GMRT is looked at any part of the sky, all of the sky, just few minutes. But when you go to GMRT, we look at that part of the sky, that initial discovery that you would get a student, we look at it for 5 hours, not 5 minutes, but 5 hours. If previously you can say mobile photography, here we will go with the digital camera, DSLR. So this way you will be discovering many more. And there is a proper hierarchy, systematic way of doing this research. Because thousands of people are involved at the basic level. There has to be a proper step-by-step growth in your career. So some one-day train, online train, 7-day train, some PhD degree holder, there are various methods there that your discovery goes to like water filtration process and goes to a publication. And everybody has to be analyzing the GMRT data, learning to analyze GMRT data and make sense, scientific meaning out of it. So ICTS helps us, feeds for 7 days. People are selected from all over India. You can spot Chiranjeev here, I am here. Students are hosted there, they are trained, they are ready to go back to their home and continue discovering every week. In 1 day program, like ISAR Berhampur, hundreds of people can gather in 1 day and get training. Suppose this was not a 30-minute talk, but a 1 hour, 1 day talk, full 1 day talk, we could have done wonderful. In future, we can do it. Let me go a little faster. I am felicitated by many people appreciating that how students are getting involved in this learning process and discovery process is appreciated by ISAR, like ISAR Kolkata and ISAR Berhampur. Government also appreciates that you have started something interesting and innovative socio-scientific idea, and that's how I was awarded with Chief Minister of Odisha and Ramachandra Chandrasekhar Jyoti Award. Okay, that's not the point. Point is for students here. How do you start? The starting point, first step. We have a website, as I said, radiomindia.org, something called RGB Maker. You can click the tab here, that will be RGB Maker. Red, green, blue, RGB, image you will make. You put your name, put a galaxy target NGC 12, NGC 13, 398, any galaxy name, or you can put coordinate, M87, M31, many things you already know. Put that galaxy name, 4 images will come. What out of the 4 images? It combines data from optical telescope, infrared telescope, ultraviolet telescope, radio telescope GMRT, radio telescope VLA in USA. 2 centimeter wavelength radio emission, 20 centimeter wavelength radio emission. You just need to learn the uniform and minimum way is to how to understand this RGB image. For example, this is one clear statement. Here the RGB images are actually false color images will come. But the color of the stars that you see in the sky, they are all black body like things. The color that you see are because of their black bodies. Okay, like I will say in a red hot. So Wien's displacement law simply, the things which are looking bluish, they are hotter stars. Things which are looking reddish, they are cooler stars. So the temperature difference of star is coming because hydrogen is bonding to helium, they radiate by light, and if they cannot radiate, the surface becomes hotter. It will pop up. So there is kind of a balance between the radiation and the heating process. So stars color, yes.
Huh?
Not mute.
Are you sure?
Chiranjeev. Sorry about that. So here, the color is a false color here. What I have put red is 22 micron infrared that is not visible to eye. What is put in blue and green is the optical picture and ultraviolet. What you see here, that the invisible infrared emission shows something as an arc-like thing around a bright star. When the star is moving towards north, it creates kind of a wind, creates a bubble, and that bubble compresses the interstellar medium, the medium that is in between stars. It absorbs the light, the dust and pH, polycyclic aromatic hydrocarbon, that absorbs the ultraviolet light, gets heated up, and that emits in infrared. So that is this arc-like thing, red thing is not visible in green, means that is not visible in optical. So that means by combining 3 images, 1 visible and 2 invisible, we are seeing the interplay between the warm component, that is star, which is 6000 degree hot, and the cold component, that is dust, that is 300 degree Kelvin sub-zero. So this is how you have combined images and started interpreting, going beyond the visible astronomy, naked astronomy. Astronomy means not just this. Astronomy means much more than that. For example, here, this is a Kritika. Kritika is a simple stars. Star here, star here, star here, multiple stars. There are gas and dust. If you go to infrared, that is in red. That infrared is brightly shown because the gas that is absorbing is cold. Stars are 6000, your gas is 200, 300 Kelvin. What are the white lining blobs that you see? It's actually something else entirely, that is a radio. So the stars are not seen here because stars are black bodies. Black body radiation curve, you know, it rises, has a peak and falls. In peak in the optical because there is 6000 degree hot around that. But there is another kind of radiation which is not this constant rise and fall like black body spectrum, Planck spectrum. There is a different, a straight line. This is very, very strong radiation in lower frequency of radio, and it falls in higher frequency radio. That kind of thing is coming next. So this is the same Pleiades constellation. This is a radio galaxy. Radio galaxy, stars, old star, young star, dust, gas, everything is confined. Like Professor Saikia described, the plasma jet from the black hole accretion process goes far out of the galaxy. And that is seen in radio. So the Pleiades constellation, the stars are black body, but the non-thermal emission for the background active galaxies, radio galaxies, can be seen in this pink area. So the GMRT doesn't see this bright star that even naked eye can see, but sees the plasma ejected by black holes in the far, far away galaxies. Oh, amazing thing. That's how the beginning of the astronomy starts with GMRT for any member. That you start seeing completely different. That you think astronomy of understanding Kritika Nakshatra Punja is your astronomy. Ursa Major is your astronomy. Orion is your astronomy. But we see have a different telescope, we see different things. Okay. So I think 20 minutes passed. Let me give this quick thing. What we see with GMRT, what you can enter as a radio astronomy in citizen science, that is our purpose. This is M31, Andromeda Galaxy. Stellar light, young stars, old star, ionized gas, H-alpha emission that you can see in the pink region. So different wavelength, if you go, you see different temperature component and different physical component of the galaxy. For example, if you go to X-ray here, if you go to infrared, if you go to optical, if you see different component. If you go to infrared, as I said, you see the dust and pH, which are frozen systems. You go optical, you see stars. Go to X-ray, what do you see? You see things which are million degree, 10 million degree hot. Only then they are emitting maximally in X-ray. Things which are cold, emitting maximally in infrared. Things which are warm, emitting maximally in optical, that is star. So different wavelengths are giving views or dynamics or cause in different phases of matter. Very hot plasma stage, cold frozen stage, warm stars, and here gas. Another component. In RGB images that I have described you, you put the same thing now together. Ultraviolet in blue, infrared in red, optical in green. What do you see? The spiral arm of this largest spiral galaxy is bright in ultraviolet. That shows O and P type stars which die of in few million years. They are hot, 20,000 degree hot. That's why the emission peaks in ultraviolet. This I have ascribed 200, 300 degree Kelvin cold. This is stars. So by just because of an RGB image understanding, you have developed your expanded your understanding of Orion constellation or M31 in optical picture to a multi-wavelength image analysis. Let's go. So apart from those kind of images, you have also spectra. I will not go much detail, but quickly that you have this blue, red, green, whatever emission coming from the black body of the star, galaxy which is 100 billion stars, you along with the continuum emission of the black body of various stars, you have emission lines or absorption lines that Professor Saha helped us to understand, making astronomy to astrophysics almost. So what does it mean? That we can narrow down in our understanding of frequency range. There's a full rainbow, VIB, GYOR, but you analyze narrow band, say for example, sodium D1, D2 line. Then with a grating or a prism, you narrow down your analysis range. That becomes a spectral analysis, spectroscopy. That was imaging, this was spectroscopy. Now, you must have...
Professor Gupta, you have 5 minutes left, so then we'll have to...
All right, we'll finish in 5 minutes. So from Niels Bohr's model, when electron jumps, you get H alpha, H beta, H delta, different spectral lines. Looking at where the spectral lines should appear in the laboratory and where the spectral line appears from a galaxy or a star, the difference gives you the velocity at which the line emitting gas is moving towards you or away from you. This is Doppler effect simply. So if you look at a galaxy's hydrogen gas, Professor Saikia also explained this, when electron and proton, classically one can imagine, they are in the ground state. Both of them are parallel spin or anti-parallel spin. They have slightly energy difference. Anti-parallel spin is stable, parallel spin is slightly unstable. So if you want to flip that spin flip transition, the energy difference is so low that the line does not come in the optical UV IR anywhere, but in radio. So that atomic hydrogen that is emitted by hydrogen gas surrounding this optical light of stars is much bigger, and that one can analyze and see the velocity field by using Doppler shift method. The line which are supposed to be appearing here, 21 centimeter, it can appear somewhere else. So analyzing that, you can get a velocity field of the galaxy's hydrogen gas, neutral atomic hydrogen gas, GMRT can observe. One side will be red shifted, another side will be blue shifted. That is how you measure the velocity, how the galaxy is rotating, how its mass can be derived. Okay, so from there dark matter concept has come that the galaxy's gas is rotating very fast, likely because it is surrounded with a dark matter halo. The schematic picture, we have not seen dark matter. So I don't have much time, but I will give you one simple, quick answer to the last point that I will to say. What is the last point? So this is a giant elliptical galaxy. This is like Milky Way galaxy. So tens of galaxies may have merged to make a big demon galaxy like this. When such a galaxy creates this kind of plasma jet, radio jet, what it does when it was going out, that's an important point. That is called AGN feedback. That the radiation, the plasma that is going out from the black hole separation process, what it does to the galaxy. In a schematic I can explain you. When two galaxies merge, such kind of outflow can happen. Jet outflow can happen and push aside the cold gas of the galaxy. From cold gas only new star forms. So the simulation that I have showed in the beginning, that how jet hits a galaxy, if you understand how jet affects the cold gas of a galaxy, we may be able to understand why this kind of spiral galaxies have blue star formation happening currently today. Spiral galaxies, a lot of star formation, young star formation happening today, and elliptical galaxy star formation not happening. That's why they are all looking yellow, like our sun, 4.5 billion year old yellow star. All the stars in the elliptical galaxy are very, very old. So if we understand how the jet outflow affects galaxies' gas, we'll be able to understand probably how black hole play it all by removing cold gas, new star formation happening in spiral galaxy, in making probably elliptical galaxies red and dead or old with all old stars of several billions of years. This is a big puzzle, and AGN feedback understanding is that's why very important. Okay, so that's not much time, but looking at the spectrum of stars, how old they are. The galaxy is looking bluish, it is million-year-old stars, very young stars. The galaxy is looking reddish, they are very billions of year-old stars, they are very old. Similarly, very quickly I will describe you this. By looking at optical radio images, red will be GMRT image, blue will be American VLA image, how bright it is in low frequency and how bright in high frequency. By comparing that, you kind of get a spectrum. And from that spectrum, low frequency, high frequency, bright and fainter. Looking at the relative brightness from American high frequency data and Indian low frequency data, we can find out, Chiranjeev is an expert in this field, to find out how the plasma lobe that has gone out of the galaxy, how old they are, since when that is cooling. To figure out that, if you can do that, then we are kind of age dating the plasma outflow process from black hole. And by looking at the optical light, we are going to age date how the stars are young and old. So how the galaxy and the black holes are co-evolving together, how they age, we'll be able to understand. By looking at this outflow, students are finding the old outflow from the data. Old outflow, the kind of black hole archaeology, and that is how we want to solve the black hole galaxy correlation study, by spotting old outflow from black hole in red, green, blue RGB images made with GMRT primarily. Spot it from home. We will follow up with the GMRT. We will follow up many other telescopes and we will publish paper together. So students, citizens, and professional astronomers are kind of empowering this society through big telescopes that we have in our country. I think I will stop it here. Not much time, except that we have made a lot of news, but that is not important. What is more important is how you people can be part of that discovery making publications and news. News only inspire next generation of students. We are here to help you pass on the data. Thank you very much.
Okay, so thank you, Professor Hota, for very nice presentation, and whatever more importantly, very like what you are doing actually, this is commendable. Like right at home, I heard long back about this thing, but I have not got to like attend any of the talks or anything. So meanwhile, we have some questions, so we can go one by one. So I'll read. The first one is Boichak. So his question is that, is the radiation from the galaxies ionizing or non-ionizing?
Okay, so it depends actually which radiation you are talking about. For example, if X-ray or UV radiation is coming, you know what is the if it is 13.6 electron volt and above, it can ionize the hydrogen. So ultraviolet and X-ray radiation coming from any sources is ionizing, but there are other radiations which do come from dust and optical stars that I said, or radio radiation. They are not ionizing. They cannot ionize even hydrogen. It depends which atom, which molecule you are talking about, which radiation you are talking about.
Okay, okay, I think it is clear to him. So another comment from Sulagna Samant. So he's asking, as a part of ACTI at home, it would be great if you come to campus at Calcutta University if our head grants permission. So yeah.
It's not SETI at home, it is read at home. And okay. There to ISER Kolkata, okay. But any moment anybody can welcome us. online or physical participant, anything is all right. We are ready to help. Just try to me or to
Dr.
Sorry for the interruption. Vibhuti, there are few students who would like to ask directly from here. We have lots of students sitting here, so they would like to ask questions physically from here.
Yeah, that will be great. So yeah.
Can they?
Yes,
They
So there
can
are
come
so
forward
many
directly.
students are sitting. They are sitting here and listening to it, and they would like to ask questions.
yes. Please go ahead.
So can we call them?
Yes, madam. You just call one by one. Tell them who should ask.
Dr. Vibhuti.
Yeah,
Will it be okay?
please go ahead.
Okay, please come one by one. You can just come here and ask.
Hello, sir. My question is that we've heard that if a matter cannot travel at the speed of light because its mass keeps on increasing. So we've also heard hypothetically that universe is expanding at the speed faster than light. So don't these two things contradict each other? Like universe is made up of matter. So if they're expanding, then there would be a mass. So how do you explain like at one point we are saying that mass will be increasing, but at the other the universe is itself increasing?
Okay, there are few things. There is no a single answer to this. One thing is that in astronomy we observe few things moving faster than speed of light. There is a kind of illusion called superluminary motion. The other question that you are having to answer: when something moves, it moves in the space. Its space coordinate changes, so it is moving in the space. But when we say cosmological expansion for universe, it is not actually galaxies are moving in the space. The space itself is expanding. So what we interpret as a Doppler interpretation of expansion, for faraway galaxies, the velocity may be seeming to be greater than speed of light. There is a wrong interpretation. The galaxies are moving in the space. What is correct interpretation is like the balloon analogy. Some three ants are sitting on a balloon and you blow the balloon. Balloon expands. Galaxies are not crawling on the balloon surface. Ants are not crawling, but the balloon itself is expanding. So the space and time, both are actually expanding. Like time is moving, we understand it easily. But when you say space is expanding, we don't kind of understand what does it mean. But that's what physics is currently. Okay, so there is no contradiction in that sense.
Okay, so any other questions from student side? I think there is no.
Just one question, please.
Okay.
Yeah.
Good afternoon, sir.
Sir,
first of all, that was a really interesting lecture that you gave. My question is, during the merging of galaxies, like you said, some plasma waves are released, right? So which galaxy specifically like releases the plasma wave, or both of them do? And what's the reason?
It is not plasma wave, it is the plasma itself is released. So actually the capacity to release such jet plasma is there in both the galaxies. At the same time, all the big galaxies, there is massive black hole. But for this particular case, red 12 that we are showing, recently published, the smaller galaxy is seen to be releasing a plasma jet. That does not mean sometime back or in future, the bigger galaxy cannot create a jet. That also has a bigger black hole. It has also the capacity. We do not know. We say what we are seeing it. But in other cases, absolutely fine that during merger process, both the galaxies can also be having such kind of jet outflow. It is possible.
Yeah, thank you. Any other question from students directly?
One last question from a student.
Yes.
Please ask in a short manner to get him. So my question. So my question is that is it does there is a possibility, or is there is a possibility of a spherical galaxy, because the things which you have told is about only the spiral ones. Is it the possibility there because the center of the galaxy is a supermassive black hole and the gravitation works in every dimension? So is it possibility to have a spherical galaxy kind of thing?
Yeah. So correct. The word is the galaxies come which are spiral. They are actually flat, like a mobile screen. Their thickness is very low and diameter is very large. For example, our galaxy can be 1 kiloparsec thick, but could be 10 kiloparsec this way, 10 kiloparsec this way, 20 kiloparsec big, like Uttapa or Dosa you can think. But the elliptical galaxies are like balls, From which direction you see, you don't really know, but they are seen as kind of ellipsoid. Either they are squashed, pressed from the top, or elongated this way. So oblate or prolate. These are called triaxial galaxies, A, B, and C. C can be smaller than A and B, or C can be longer. So galaxies, what are the exact shape? We cannot go behind the galaxy and see from another angle. They are too far away. So kinematics helps us to understand that there are flat galaxies which are spiral galaxies, and there are triaxial ellipsoid galaxies which are sphere-like thing, not exactly sphere, ellipsoid. They are elliptical galaxies. So the supermassive black holes are sitting at the very center. They are supermassive, million to billion times mass force one. But as the X-ray image I was showing, there are small black holes, stellar mass black hole everywhere in the galaxy. All the X-ray point sources, maybe Professor Dipankar Bhattacharya will be talking about them. There are small black holes everywhere in our galaxy. Wherever there is a big star explode, there can be a neutron star or a black hole. And there is another star nearby, it will be brighten up to 1 million degree and it will become an X-ray source. The point sources in the sky, in our galaxy or M31, they are stellar mass black holes. Supermassive black holes are only one, most of the cases, at the very center of the galaxy. Bigger the galaxies, balls like elliptical galaxies have bigger black holes. Smaller spiral galaxies will have smaller black
holes. Okay, thank you. I think we are running late. So, but I have a quick question, since I am not in the field, but related to. So, how do you model exactly the cosmic ray muons or cosmic ray or neutrinos, for example, with AstroSat or any satellite-based experiment? Like how you measure their composition and all?
I am not an expert to understand on this neutrino or muon thing with AstroSat. What AstroSats actually observe is very high energy X-ray emission. So it is not a particle detector. So AstroSat helps in modeling the X-ray emission, high energy X-ray emission from black hole accretion process or neutron star accretion process. You can, there may be some way of mapping this hard X-ray emission to the neutrino or kind of some other particle emission from there. There may be kind of a scaling relation. I don't quite know, but AstroSat is not a particle detector.
Yeah. Hello.
I am not an expert in that field.
Okay.
Hello.
Thank you.
Hello.
Thank you,
Hello.
Yeah, Professor
Dr.
Suresh Chandra wants to ask something.
Yeah, one question I may ask that, because am I audible?
Yes.
Yes. Dr. Hota, it was very good talk, but just you mentioned that smaller galaxies will have a small black hole, and bigger galaxies will have big black hole. But the size of the black hole goes on reverse to the mass of the black hole. Hello?
Yes, I can listen.
Could you listen my question?
Yeah. What I colloquially said, a bigger black hole is their mass of the black hole and the mass of the bulge part of the galaxy are correlated.
No, you just mentioned to the answer for answering a question from the student that smaller galaxies will have a smaller black hole and bigger galaxies will have bigger galaxy hole. Is it in terms of the mass or in terms of the size? My question is this.
I am sorry, I should have said the smaller, less massive galaxies will have less massive black hole, and more massive galaxies will have more massive black hole.
Yeah. I thought that, yes. Okay. Thank you. Now it's clear. Yes.
Okay.
Thank you.
So,
Thank you.
Yeah. So if there is no questions, let us thank the speaker, Professor Anand Hota, for very interesting talk. And I would also like to thank Dr. R.K. Chobe for introducing the speaker. So with that, let us go to the next speaker, and Dr. Adarsh Kumar will.
Thanks, Anand.
Introduce the next speaker.
Yeah.
Adarsh sir is there.
Thank you, Dr. Parida. Am I audible?
Yes.
Yeah. So guest speaker for this session is Dr. Pritam K. Das. So first, Dr. Pritam K. Das, I welcome you in this great workshop of astrophysics. So Dr. Pritam K. Das, he is working currently as associate professor in Department of Physics, Pabna University of Science and Technology, Bangladesh. He has obtained his MSc in physics from University of Rajshahi, Bangladesh, and a PhD from Okayama University, Okayama, Japan. His field of research is nuclear physics as well as nuclear astrophysics. He has published over more than 30 research papers in different reputed journals. He has been awarded Froza Malik Scholarship in 2009. Moreover, he acquired NSICT Fellowship from the government of Bangladesh. He is working in collaboration with Dr. P.K. Datta of IIT Kharagpur, and for his work he has got a scholarship from the international university. Moreover, he is a member of Bangladesh Physical Society, BPS, as well as he is a member of American Physical Society, APS, USA. In spite of it, he is a member of various research groups working in plasma interaction. Moreover, he was a member of various departmental duties in his university. He has worked as chairman of the Department of Physics, moreover as proctor, and other duties also. So today he will deliver a lecture on role of nuclear physics in unraveling the mystery of evolution of universe. So Dr. Pritam Das, so now you can deliver your talk.
Yeah, thank you, sir.
Yeah.
Thanks, Dr. Pritam. Thanks, Professor Pritam. We are very happy to have you here. And from Bangladesh, we hardly do any collaboration, even though we are a neighboring country, and we hope that we will go long distance with you.
Yeah,
Please go ahead.
Love to, sir. So I'd like to thank the authority of this great workshop entitled the Workshop on Recent Progress in Astrophysics, a tribute to famous Professor Dr. Meghnad Shah, sir. So actually, this is the great opportunity for me because we know that Professor Shah actually was born in Bangladesh, so near Dhaka. And, yeah, so I'm proud to be the same part. So I always actually feel proud his work. And so today it's a great opportunity because this workshop actually dedicated to his name. And actually I designed my lecture for undergraduate student. So I think this may be the very basic, but I'll try my best to show some interest because there's some role of nuclear physics. So in knowing the universe evolution and the astrophysics. So I'd like to say something about that. Can I share my slide?
Yes, please.
Okay.
Can you see the share button or no?
Yes, sir.
Yeah, please do that.
So thanks again, the authority, for giving me opportunity to say something in front of you. 1 minute. So title of my lecture is the role of nuclear physics in unraveling the mystery of the evolution of universe. And my name is Dr. Pritam Kumar Das, Associate Professor, Department of Physics, Pabna University of Science and Technology, Pabna, Bangladesh, and currently working as a visiting scholar and senior instructor, Department of Physics, Eastern Mediterranean University, Northern Cyprus. So this is the outline of my lecture. So first I'd like to introduce something, and then history of nuclear physics, properties of nucleus, nuclear reaction, evolution of the universe, Big Bang nuclear synthesis, nuclear reaction in stars, supernova nuclear synthesis, and what next, and then conclude my. So we know that nuclear physics is a branch of physics, and it's this is the field of physics that studied atomic nuclei and their constituent and interaction. So in addition to study the other form of nuclear matter. And nuclear physics is the study of proton and neutron at the center of the atom, the interaction that hold them together in space just few femtometer, that means 10 to the minus 15 meter. And we can see the example of nuclear reaction include the radioactive decay, fission, fusion. And we have some confusion about the atomic physics and nuclear physics, so we shouldn't do that. We should not actually confuse with the atomic physics and nuclear physics. So as we know that our present understanding of universe is based upon the successful hot Big Bang theory, and which explain the evolution from the first fraction of second to the present age, and which is about 14 billion years actually later from the Big Bang. And understanding our universe from the basic physics is an ambitious goal involving many disciplines in physics, and one key ingredient is nuclear astrophysics. The role of nuclear reaction in our universe is twofold. One is the production of energy, and another is the formation of element, that means the nucleosynthesis. And in this lecture, I'll try my best to find out the role of nuclear physics in unraveling the mystery of the universe evolution. So this is the very actually the famous picture that the origin of the universe. You can see we started from the Big Bang, and this is the Planck era, and in this region, this is the dark region, all the Big Bang nucleosynthesis and the quark-gluon plasma state. And the first, actually, the star appeared after 300 million later, and the first galaxy actually appeared 1 billion year later from the Big Bang. And today we are here about 14 billion years. So at the beginning, in the universe, there were same amount of matter and antimatter, but if we see now, the condition is that the matter is dominated, the antimatter is disappeared. So the scientists are trying their best to find out the region where that antimatter is gone. And so here also there is a big role for nuclear astrophysics. So before going details, I'd like to say something briefly about the nuclear physics, basic nuclear physics. So we know that all the matter actually made of atom, and inside the atom we know that we have proton, neutrons, and electrons. So protons and neutrons actually exist in a dense core, the center of the atom, that is called nucleus, and electrons are spread around the edge of the atom, and they orbit the nucleus in the layer shell. So here this is the nucleus, and this is the electron are moving around, and we can see the mass, spin, and charge of neutron, proton, and electron, and we can see the size. If we see that the atomic size is Armstrong range, that means 10 to the power minus 10 meter, and the nucleus range is 10 to the minus 14 meter, and proton 10 to the minus 15, and quark 10 to the minus 18. So if we see the ancient some ancient view of atom, so the early theory was the Aristotle, and he thought that all matter flows continuously and is composed of 4 elements, that means fire, air, earth, and water. But Democritus actually disagree with Aristotle and said that matter was made of the small unit called atomos, and that were invisible. So this is the chart where up to Dalton, so this Aristotle 4 element was staged. So, but after 1803, Dalton actually give his model, and we can see what he said. All the elements are composed of atom, and they are indestructible like a solid sphere, and they cannot be created or destroyed of conservation of matter. So atoms of the same element are exactly alike. Atoms of different elements are different, and compounds are formed by the joining the atoms and so more. And then in 1897, Thomson actually discovered the negatively charged electron, and William Thomson actually proposed that atom consists of small negative electron embedded in a massive positive sphere, and the electrons were like a current in a pump pudding, and this is called the pump pudding model. And then by the alpha scattering experiment, Rutherford actually discovered the nucleus in 1908, and Rutherford reasoned that all the atoms actually positively charged particle were contained in the nucleus, and the negatively charged particle were scattered outside the nucleus. So he said that inside the atom, the center should be nucleus and electrons stay outside. And then this model actually modified by Bohr in 1913 with the help of Planck's law. Actually, what he said that a countable number of stationary states exist electron in a section of allowed orbit radii, and electromagnetic radiation emitted when the electron jumps or transits between the states. And the classical rules apply to stationary state, but not during the transition between the states. And the angular momentum occur in integer multiple is by twice pi. So this is the history of nuclear physics. You can see the started from 1896 after the discovery of Henry Becquerel, discovery of radioactivity, and in 1911 Rutherford discovered the atomic nucleus. In 1913 Thomson nuclear mass and isotope, and in 1935 in theoretical development Yoka developed the famous meson exchange model. And so nuclear properties, so we can write the nucleus as this way. So here A should be the mass number and Z is the proton number or atomic number, and charge and mass. So we know that electron has a negative charge and proton has positive and neutron chargeless, and we know how become proton is a positive and neutron, because if we break the proton we get 3 quarks, 2 up and 1 down, and if we break the neutron we get 3 quark, 1 up, 2 down. So if we put the charge of this up and down quark, we get the proton is a positive charge and neutron is a charge less, that means 0. So in atom, the binding energy between electron and proton is Coulomb force, and on the other hand, inside the nucleus, the how actually neutron proton stay together due to the very strong nuclear force. And the binding energy of deuteron, so it's 2.2 MeV, and that is around 200,000 times bigger. And size of the nucleus, so we can calculate the radius of nucleus by this equation, and we can calculate the density of nuclei by here. So here is this equation. Nuclear stability, there are very large repulsive electrostatic force between the protons. So as this force should be cause the nuclei to fly apart. So for larger nucleus, so the dominancy of the electrostatic force become larger, and the nuclei are stable because all the presence of another short range force called the nuclear force, and this is an attractive force that acts between all the nuclear particles, and the nuclear attractive force is stronger than the Coulomb repulsive force at the short ranges within the nucleus. You can see for light nuclei are mostly stable because up to calcium 40, there's the N and Z number is almost same. So as the number of proton increases, the Coulomb force actually increases, and so more nucleons are needed to keep the nucleus stable. And no nuclei are stable when Z number is greater than 83. So from here we can see there is a difference in mass when the nucleon come together and form a nucleus. So if we calculate the mass of that nucleus, we can see that the amount of nucleons and proton actually form that nucleus. If we measure that mass, there is a difference. There is a difference in mass, and that is called the mass defect. And this corresponding energy is called the binding energy. And the total energy of the bound system is less than the combined energy of the separated nucleons. And this difference in energy is called the binding energy. And this binding energy per nucleon curve is very important for understanding that two famous reaction, nuclear fission and nuclear fusion. So I'll discuss it later. So there is another thing, radioactivity. Radioactivity is the spontaneous disintegration of atomic nuclei, and we can see there are three types of radiation can be emitted: alpha, beta, and gamma. So in alpha decay, they release a particle of 2 proton and 2 neutrons. So you can see if a nucleus emit alpha decay, it will reduce 2 proton and 2 proton and 4 mass number. So and beta decay, if we have a nucleus who have extra proton and extra neutron, then that extra neutron can be converted to proton and neutron by decaying beta. So for nucleus who have extra neutron, they can convert that neutron into proton by decaying beta minus, and who have extra proton, that can be changed this proton to neutron by beta plus, or it can also go through electron capture. So this is the Feynman diagram of here. You can see this is the weak interaction. So the one down quark actually changed to up quark, and in that time there is a exchange parameter is OW minus, and there is a anti-neutrino, and electron is come out. So in gamma decay, actually for excited nuclei actually emit gamma. You can see. So this nucleus actually emitting gamma to here, and also it can emit gamma directly here. So the beta decay. So this is the nuclear reaction. So there are a lot of nuclear reaction. Let's take elastics, needed to capture photonuclear reaction, stripping. And for nuclear astrophysics, very important is nuclear fission and neutron capture. So, and to do nuclear reaction, we have to consider some conservation laws. So we have to think about the mass number conservation, atomic number, energy, linear momentum, angular momentum, parity, isotopic spin. So this is the fission, when the big nucleus actually break down into small by interacting with small nucleus. This is called the fission. So this is the example how a neutron actually interact with uranium, and this is actually used in our usable nuclear reactor. So this is the chain reaction and nuclear fusion. Now, when two small nucleus actually come together and fuse together and form a bigger nucleus, this is called the nuclear fusion, and this is the very common reaction in stars. So here you can see the nucleus. This is the most maximum, actually, the binding energy per nucleon, and the maximum one 8.5 for iodine 16. So if we go after iodine 56, we can see the binding energy per nucleon is decreasing, and from here also decreasing. So this all actually nucleus try to go in the maximum stability and go to this region. So how they can go? So this region can go here by fuse together by fusion. So here, these are dominant for nuclear fusion, and this region actually can come in this region by breaking themselves and make it small to parts, and this is dominant for nuclear fission. So neutron capture reaction. So when actually neutron actually captured by a target nucleus and form compound nucleus, and that reaction actually can go through, that excited nucleus can go through by going that nucleus is the ground state and extra gamma, and that is known as the neutron capture reaction. And this is also very important for supernova nucleosynthesis stage. So if we break the matter, we can see three main things. That means we have field particles, that means W, Z, boson, photon, graviton, and so we have a hadron. So we can break the hadron. We cannot break field particle and lepton. And in the lepton, we have muon, the electron muon tau and their neutrino and their antiparticle. That means electron, neutrino, muon, neutron, and tau neutron and their antiparticle. But we can break the meson and baryon. So in meson, if we break, we can get the quarks. So when two quarks come together, we can get meson. But when more than two, that means three, then we can get baryon, and common baryon are neutron and proton. So then why do we study nuclear physics? The question may arise. So nuclear physics is a fundamental physics for understanding our lives and the physical world around us. And we can get some answer from this question. if we study nuclear physics, what is the origin of the universe? What is the origin of nuclear? Like what we are seeing in the Earth, there up to 120 nucleus. So where this actual nucleus come from, and how actually the star form, and how actually star gets the energy. What are happening in this inside star, and what is supernova and formation of heavy, how really supernova can form the heavy nucleus. And we can understand more about the star, supernova, Big Bang, the creation of the chemical element, production of the energy in star, and the art of nuclear astrophysics. So we are all actually made from the product of exploding star, and that's why actually scientists actually call us as a stardust. So we can know the building matter and that matter falling apart. So building with quarks and lepton, that means neutron, proton, and deuteron, and nuclear, how many elements and why, star, neutrino mass, and cosmos. So this question can be answered by the nuclear physics. And nuclear processes are used to all around us, and their key application in many aspects of our lives. So nuclear fission, that means we are using it for power generation in nuclear reactor. We are trying to actually use the nuclear fusion reaction to produce the nuclear in the nuclear power plant, so that we can get more energy to solve our energy problem of Earth. So if we see that this evolution of universe picture, we can see we have started from the Big Bang, and we can explain the time 10 to the minus 43 seconds after the Big Bang, that is known as the Planck era. So as the actual temperature goes decreasing, so we can see the energy also decreasing. So we can see that there is a soup of quark and gluons, that plasma, that is quark gluon plasma stage. And as it goes more time, and the temperature fall down, and energy also, and we can see quark and some proton, muons, and neutron actually the form. And then the first actually the nuclear reaction actually come place, that is known as the Big Bang nucleosynthesis. 3 seconds, around 3 seconds, or around 1 second after the Big Bang, and it will continue up to 200 minutes. So, and then the first atom actually we can see the first atom. We can see after the 3,000 year after the Big Bang, and the first star and the galaxy actually you can see after the 300,000, and we are staying here. So we'll discuss about this Big Bang nucleosynthesis and the nucleosynthesis in star and supernova after in this year. So the evolution of universe. So before the short period of cosmic inflation, there is a cosmology belief that all matter of the universe was squeezed into the space much smaller than the atom, and we can see there is all the force actually merge into one here. As actually the time goes, first gravitation actually separated, and then in the here actually this strong nuclear force is separated, and this is the electroweak unification, and here you can see this is the 10 to the minus 15 Kelvin. So here actually you can see more detail about the nucleosynthesis. So the time of Big Bang, as the time of quark gluon plasma, the temperature 10 to the power 12, and time is 10 to the minus 6 after the Big Bang. And here proton and neutron formation immediately after that, and there is a formation of low mass nuclei. So within 3 minutes, and there is a formation of atom with 400 Kelvin temperature, and about 400,000 years later, and the formation of star about 1 billion year, and a dispersion of massive element. That means after the more than 1 billion year, we can see this stage, and today we are here. So we can divide it the nucleosynthesis in three. types. So first is the primordial nucleosynthesis, and there is stellar nucleosynthesis and supernova. So primordial nucleosynthesis is the nucleosynthesis immediately actually happened after the Big Bang, and from here we can get up to the lithium. So no heavier element can form in this Big Bang nucleosynthesis. In stellar, the nucleosynthesis which had happened inside the star, and here we can get up to iron. But in Earth, and we know that there is about up to 120 or 21 number of elements. So where those actually come from? So actually those nucleus actually can form after the supernova explosion, that is called supernova nucleosynthesis. So this is the Big Bang. So here the first reaction, so when a proton and neutron come together and form a deuteron, and if this deuteron actually come together and they actually form 3 helium and neutron, and this 3 helium also can interact with 3 helium and can form 4 helium. Or we can get helium-4 by 3 helium with this tritium with neutron, and this tritron with proton, we can get 4 helium also. So there are several important characteristics of Big Bang nucleosynthesis. The initial condition, that means the neutron-proton ratio, is very important here, and were set in the first second after the Big Bang. And the universe was very close to the homogeneous at this time, and the strongly radiation dominated. And the fusion of nuclei occurred between roughly 10 seconds to 20 minutes after the Big Bang. So, and here the most dominant nucleus are hydrogen, about 75%, and helium 24%, and lithium, after lithium, or just 1%. So from here we can see there is a stage, we get atom, and then from the cloud, stellar cloud, we get the star. So then this is the evolution of star. So here in this region, how actually all the matter in the stellar nucleosynthesis are come, we need to know. And after here, after the supernova, there is other heavier elements actually come, we also need to know. So the basic nuclear reaction in the sun actually convert the hydrogen and helium and releases the energy in the form of electromagnetic radiation. And the star actually heavier than our sun actually can fuse heavier element. And if we see, this is the onion layer, we can see when the fuel of hydrogen actually finish, then we have a helium dominated core, and then if we have that environment, that means the temperature and energy, they can start the helium burning, and by burning helium we can get the carbon rich core, and then if we have that environment, then we can start the carbon fusion. So and up to this we can get iron by silicon burning. So but there is no way to burn iron. So we can discuss and why this is. So this is the basic reaction in star. First reaction is two proton fused together from deuteron, and this deuteron can interact with the proton and form a 3 helium, and 2 3 helium can interact and form a 4 helium, and by this way the star can be dominated iron helium in the core. So this is the two famous reaction. One is the PP chain reaction, another is CO cycle, carbon nitrogen oxygen cycle. You can see here in PP chain reaction, one hydrogen and another hydrogen fuse together and form deuteron, and when these deuteron interact, another hydrogen form 3 helium, and similarly this happen, and when these 3 interact and form helium, and we get this hydrogen again. So this is the chain reaction, that this is known as PP chain reaction. And here also you can see this is the CO cycle. So when 12 carbon interact with hydrogen, it forms 13 nitrogen, And you can see this 13 nitrogen is unstable, so it will decay beta plus, and it will form 13 carbon. And this, when this 13 carbon interact with hydrogen, it forms 14 nitrogen. So this is going, and from here, so when this hydrogen interact with 15 nitrogen, and then we can get 12 carbon and helium. So this is also the chain reaction. This is known as the CO cycle.
Okay, so Professor Das, so you have 5 minutes left. So please
Okay. So this picture actually, why this is important. So I told previously that so we can explain that in the star core we can burn up to silicon, but no way to burn actually the iron. So the thing is that if we see here, so if you fuse actually 2 iron, then it will go like this region. So no actually nucleus want to go the unstable state, or that means here binding energy per nucleon curve, you can see the binding energy per nucleon is less than this, so there is no chance to go here. So that's why it's very it's not possible to burn the iron. So we cannot get the heavier nucleus after iron during the stellar nucleus. So we need a supernova explosion. So supernova nucleosynthesis is the nucleosynthesis of chemical element in supernova explosion. So here the role of neutron capture actually is large. You can see there is a slow neutron capture called the S process. Slowly it can capture the neutron and form the other isotope or other nucleus, and there is a rapid neutron capture, that is the R process. So this is the S process, slow neutron capture, and there is another proton capture reaction also. So by this 3 process, we can get the heavier nucleus. So here you can see, so after the Big Bang, so we just get these 3 elements, and from here we can get the star formation and the starting of burning, and we get the stellar nucleosynthesis. And at the end of the star, we have supernova for star who have mass more than 8 solar mass, and from here we can get nucleosynthesis that is known as supernova nucleosynthesis. And if you see our the elements, so where they are come from, so you can see the Big Bang are just hydrogen, helium, lithium, but up to here this line is for stellar, but all from up to here come from after the supernova, and this is the RP process, P process, S process, and R process. So this is the periodic table actually mentioning that where actually this element actually come from. And if we see the matter actually composition of our universe, you can see so we cannot know actually 96% still that. So we have to actually understand that what are those. So though it's known as dark matter and dark energy, so scientists are trying to find out what are those. And if we can understand, we can understand more details about our universe, and why actually we need to know, because you can see in universe actually more dominant are hydrogen and helium, and heavier element are very few. And if we see in our human body, we have different heavy element, but we can see after the Big Bang we just get hydrogen, helium, lithium. So the material actually made human that should come from the star. So that means we can call us as a stardust. So what next? Actually, the big question still actually we need to find out. So why does the universe have matter? Because initially after the Big Bang there is a symmetry between the matter and antimatter, but the antimatter has disappeared. So we need to find out the reason. And another question: how were the elements made in the Big Bang? And another question: what is the nature of the physics beyond the standard model? And I think we can get answer from the Newton experiment, and this experiment, that the EDM, can help the baryogenesis, and Newton lifetime can be help to understand the Big Bang nucleosynthesis. So another thing, we need to solve the dark matter, dark energy problem, particle beyond the standard model, and also anti-particle disappear things and quark gluon plasma things. This is actually the conclusion. So nuclear physics is an important pursuit because the study of nuclear physics atom is the heart of our ability to understand the universe, and it provides answer and expand our knowledge to both our infinitely small and extremely large. And this application include the device and technology of medical diagnosis and therapy, energy production and explosion, safe and national security, and for the analysis of material and environmental contaminants. And nuclear physics and its application fuel our economic vitality and make the world and our lives safe and healthier. So thanks all, and thanks the authority for giving me this opportunity to say something.
Thank you, Professor Das. It's a very interesting lecture covering all aspects of kind of nuclear physics, astroparticle, astrophysics, and all, and what is their social impact, benefits, and all. So I'll go to the students first. Maybe they are hungry. Maybe they can. There is a whole bunch of students that are sitting in a room. Some students can come forward and ask questions.
Yes, two students want to ask the question. Please come in front.
Yes, please go ahead.
Sir, so my question is that how is it possible to have radioactive element? Because we know that fusion process just stops at the iron, and after the supernova explosion, you said that after the supernova explosion there is an electron capture process by which
not electron capture, it's a neutron capture. Neutron and proton
Okay.
capture, not electron capture. Sorry.
Oh yes, sir.
Okay. Sorry, you can carry on.
So how is it possible to have the elements after Fe, like uranium, thorium, other things?
I'm talking about. So you can see from that curve, the Kramer's curve, the binding energy per nucleon curve. So there is no option to fuse together. So and there is actually the big thing that's happening in the big star, that means supernova explosion. So in that supernova explosion gives you that environment to capture neutron and capture proton and something like that. So by this process you can there is a three process. That means there is if you can capture proton if you have that environment, and if there is another thing, neutron capture in slowly and neutron capture rapidly. So the environment, if you get there is a denser neutron, that neutron density is higher, you can get the rapid, that means R process. But there is a less denser neutron area, you can get slow neutron capture. So by this way you can get the heavier element, those we are getting in Earth, like uranium, gold, and those actually cannot form in the star. Okay, thank you for your
question. Okay, sir, thank you for your answer.
No, I have a question. Hello.
Good afternoon.
Okay, sir. Yeah.
Sir, I'll be coming with you. I'm coming to you. So there is a student question.
Yeah. And if there's only two quarks, then the third one just seemingly pops up out of nowhere. Do we have any reason for why that happens or how that happens?
So could you please repeat, because there is a sound problem in the beginning. There is a two quark. I do not understand. Could you please repeat it again?
So we have two, like we know that quarks exist in a pair of threes, and if there's only two, then I heard that it seemingly pops up out of nowhere. They're not stable at just two quarks.
No, actually we cannot get single quark due to the confinement theory, but we can get two quarks. When two quarks come together, we can get the meson thing. So, but baryon needs to have three quarks. That means proton, neutron, So that baryon, all the baryon actually need 3 quarks, but we can get meson on those actually have 2 quarks, but we cannot get single quark. Okay, thank you for your question. Sir, maybe Suresh sir.
Yes.
Morning,
yes.
sir.
Yeah. Am I audible?
Yes.
Good morning, sir.
Yeah.
One
okay.
last question, sir. Please ask.
Okay, you
Morning,
take from
sir.
the student.
So my
Okay.
question.
Okay.
So my question is that what role does nuclear physics play in the unification of quantum mechanics and general relativity? Like, how does it play the role in it?
Okay, so I don't have that idea. So sorry, because what's your question again? There is a.
Can you unmute?
So my question is that what role does nuclear physics play in the unification of quantum mechanics and general relativity? So I'm asking, like, how does it like play a part in it?
Cannot say exactly. Yeah, I think in the panel anybody can help this.
I think he is maybe referring to quantum gravity, and that the quantam gravity people can say where they are. String theory, loop quantum gravity, loop quantum theory people can say that. We don't deal with such things.
Thank you for the question. I think they can answer.
Yeah.
Yeah. So now let's go to Professor Suresh Chandra sir.
Sir, maybe you are muted. So unmute please.
सर आप अनम्यूट कीजिए सुरेश चंद्र सर.
Maybe he's in a call, phone call maybe. So let me ask one question from the chat box. So it is from Dr. Ravi Narayan Panda from SOA University, Bhubaneswar. So his question is that why the light nuclei don't undergo fission and heavy nuclei like fusion?
Okay, so for that we need to go that binding energy per nucleon curve. So for low nuclei, you can see, so they have binding energy per nucleon is less. So they cannot, when you broke them, the fission means that means they broke into smaller pieces. So if we broke suppose oxygen 16, they can go helium-3 or something lesser actually element. So and they have less binding energy per nucleon, but they do not want to go there. They want to go higher state. That means the maximum 8.7 range. So that's why they can share like a fusion. So they can share their binding energy and they can make a stable one. And on the other hand, you can see for heavier element, they have binding energy per nucleon, binding energy is less than iron 56. So that's why they want to go in this region. That means near about iron 56. So how can they go? They can go by breaking themselves into smaller pieces. So that's why these two things are dominant. So in higher number actually nucleus, you can see the fission. For low mass or low nucleus atomic number nucleus, we can see the fusion.
Okay, thank you, sir. So may I ask Professor Suresh Chandra sir, can you please unmute and ask your question? Professor Suresh Chandra sir, can you hear me?
Just wait for a minute. I'm just going to inform him.
Yeah.
क्वेश्चन तो पूछ लीजिए. अरे क्वेश्चन में पूछ लूंगा. हाँ, हेलो.
Yes, sir. Please ask.
Hello, sir.
Sir.
Hello, doctor. I am sorry to make you wait.
No, sir. It's okay,
yeah.
sir.
Okay. My question was that you said that we cannot go in the nucleus of the stars more than the heavier than the iron, because hello.
Yeah, because
So,
the
because two iron nuclei cannot combine,
yeah.
and
Yes.
it will, if they combine, then
They
they
will
will give
destroy
the
immediately.
they will be unstable nucleus,
Yes,
right?
yes,
But
yes.
my point is that it may be something else, because we can combine the iron with some lighter nuclei, for example, helium.
Yeah, but still they can go the range. You can see they can go the range.
Because no, point is that iron has been built there, constructed there, then this iron can combine with the helium.
Okay,
Not
but
necessarily.
the when we see that is that is after the silicon burning, we get the iron rich star. So
Right,
if we get that environment, we can see some burning, but immediately it will destroy.
No. Carbon, helium, iron burning means you are saying that the two iron will combine.
Yes.
But my point is that one iron nucleus can combine with the helium nucleus.
Helium. But okay, but
and that will not be unstable. That will be stable again.
But we cannot gauge after the iron.
No, my point may be that there the temperature is not sufficient
yes for helium capture or something.
Yeah. So that may be the reason, not that two iron cannot combine, and it will make the unstable nucleus.
Yeah, temperature also a big factor. Thank you, sir.
No, temperature may be the only factor. Not only big factor, temperature may be the only factor, because temperature is not sufficient for the capturing of even the smallest nucleus to the iron, maybe the reason. But not combining the two iron nuclei, right?
No, fusion means iron fusion. Iron burning means that two iron come together. That's actually I talk.
No,
but there is a capture. You can say that you told that there is a capture can.
Professor, we have reached to the iron by capturing smaller nuclei.
Yes.
Not capturing the same nuclei, not combining the same nuclei.
Yeah, we have.
So we can continue the process, but maybe the temperature
is the factor. Yes.
Maybe yes. Okay.
Yes.
Thank you.
Thank you, sir.
Thank you,
sir. Thanks for your submission, sir.
Thank you.
Very nice discussion.
Yeah.
So there are many questions actually. It's very difficult to go all.
Yeah, we have to now wind up this session.
Yeah.
And
for lunch.
What time should we meet?
Maybe
14:10.
No, I think we can continue the same time. Those who want to take lunch, they can take lunch.
No, but we have to give the quiz, right?
Okay, you give the quiz. And after the quiz, after you take the time for the quiz, not for the lunch.
Okay, so now from now to 13:25 there will be quiz, right? I just
right.
I just paste the link. Okay.
Okay.
Can you check if the link is very visible?
Yeah, we can see.
To everybody, I have made it visible. So participants should. Can you just check open? If it is open, everything is fine. So participants, you should answer the you should take this quiz and submit it, and based on the performance, we will decide whom to give certificates, etc. And we will meet at around 13:25. So 1:25 p.m. right?
1:20. Okay. Thank you, Dr. Konar.
Yeah. So okay. So quiz will be over automatically at 13:25 hours. Whatever you can answer, you can answer. I'll just put a time limit over there. So if 13:25 is over, you cannot submit it.
Okay.
So I'm putting
Thank you. Okay. Dr. Pritam Kumar Das, very good. I enjoyed the lecture.
Yes, my pleasure, sir.
Yes, okay. I enjoyed the lecture.
Yes. All the speakers we have enjoyed. So Pritam Kumar Das, we will talk about our further action later. Okay.
Yeah. No, yeah. That is not a platform for further action.
No, not here. Not here. We will just talk about outside this.
Yeah.
And we are very happy to have you here.
Okay.
Yeah. We are happy. Definitely, we are happy. This we can say. Yes.
Okay.
Okay, so let me thank again to all the speakers and all the panelists and the audience, especially the students. So it's a very nice session, and it's pleasure again to host you at some point of time in our institute, and looking forward more interactions like Dr. Koran sir has mentioned. Okay.
Yeah, we should give a clapping too.
Yeah.
Yes.
Thank you, sir. Thank you.
So all the participants and panel member, you should not log it out. You just keep it mute and just let it be in the platform. Don't log out. All the participants and panel members.
Know that it is online. So I have taken her to that room and I asked to sit and listen the lectures. And I said that now Professor Yashwant Gupta, director of NCRA, is going to speak. And she was very happy because she is working in radio astronomy in Japan.
Oh, okay.
Yeah.
Okay.
So Professor
Yes.
Chandra, let me just announce one thing to the participants.
Please go on.
Participants, have you come back after lunch? Can you just write in the chat box, yes, whoever has come back, so that I can understand that, okay.
Dr. Konar, our all students are sitting in 401.
No. All students are okay, but those who are outside, I'm just asking them. Yes.
We had given the time and they should adhere to the time.
Yeah. Just I'm saying we are just being kind to them. Okay, so it seems a lot of people have come back actually.
Yeah.
After lunch, they are anyway online, even if they are having lunch.
Yeah.
So let us start our afternoon session.
Right.
And the first speaker of the afternoon session is Professor Yashwant Gupta. I will be introducing him. Professor Yashwant Gupta presently is a distinguished professor and center director of National Center for Radioastrophysics, Pune. NCRA is a center of TIFR basically, whose headquarters is in Mumbai. He is the Indian representative in the International Square Kilometer Array Project since 2010 and the science director for India on the SCA board since 2014. This is a very important role he is playing. Indian headquarters of SCA is at NCRA, Pune, where he is currently working. Square Kilometer Array India Consortium has been formed for the SCA consortium. Obviously, he is the representative from NCRA to the consortium. Professor Gupta has obtained his bachelor degree in electrical engineering from Indian Institute of Technology, Kanpur in 1985. He then went abroad for his further education. He did his MS from University of California, San Diego, United States in 1986. And then he did his PhD from the same institution and finished it in 1990. His research interest is diverse. He has interest in pulsar astronomy, pulsar searching, timing, emission properties, etc. And interstellar scintillations and properties of interstellar medium is also of his interest. And radio astronomical technique, including novel experiments with the GMRT, he is interested in. And also instrumentation and signal processing for radio astronomy is one of the interests that he had. He joined NCRA as a visiting fellow in 1990. Then in course of his career, he held many important posts such as chief scientist of GMRT, then dean of GMRT, then became senior professor, then became the center director of NCRA, and then he became the distinguished professor in NCRA. He is a member or fellow of various organizations. Very recently, he has been elected as a fellow of Indian National Academy of Engineering and Indian National Science Academy in this year. Further, he has been elected as a senior member of IEEE in this year itself. He was elected as a fellow of Indian Academy of Sciences in 2008. And then before that, he was elected as a fellow of National Academy of Sciences in India in 2007. He is a life member of ASI. ASI is Astronomical Society of India. He is a member of International Astronomical Union. He is a member of International Union of Radio Science. He is a member of Scientific Advisory Board and Governing Board of many institutions. There are too many to mention about his role that he is playing. He has obtained so many awards. Team GMRT has obtained Jubin Kembhavi Award in 2019, and he is the leader of that Team GMRT. Shantisaru Bhatnagar Award he obtained in 2007, and Ursi Young Scientist Award he obtained in 1996, and Rotary Club Young Scientist Award 1994. Besides that, he has a lot of publication, about 160 research papers in international journals, and he has citations about 3600, so 3,600 citations. And he has supervised so many PhD students, master students, project students, and he is a wonderful person to work with. Whomsoever I have talked to, they have expressed their happiness while working with him. So with this introduction, I welcome Professor Yasan Gupta. So the platform is yours, Professor Gupta.
Yeah, thank you, Dr. Konar. I mean, that was a very generous introduction. Thank you so much. And I hope you can hear me clearly.
Yes.
So I will just try to share my presentation for the talk. And so can you see this all right?
Yes, it is perfectly all right.
Okay. All right. So good afternoon to all the participants. I hope you've had an interesting session in the morning. What we are going to move on now to is to talk about studying the universe using radio waves, which is what we do in radio astronomy. And just a brief outline of my presentation here. I'll give you some introductory background and then talk about some of the basics of radio astronomy as to what do we do, and then move on to talking about the details of what we do in radio astronomy using our own GMRT as a case study, and then talk a little bit about the future prospects where radio astronomy is headed in the future, a lot of which will be about the Square Kilometre Array project. And in the end, if there's a bit of time, that what does it take to have a career in astronomy for those of the students who are interested to move in that direction. So to start with, I think we all know that astronomy is the oldest science. It started when man turned his gaze upwards to study the heavens and try to understand what are the objects out there. So it started with the use of naked eyes. That's a natural detector for light waves that we have. But it evolved dramatically once the recently invented optical telescope was turned by this gentleman, Galileo Galilei, towards the heavens. And that completely revolutionized our view of the universe. And it's interesting just to track that a little bit in terms of the growth of optical telescopes through the ages. So if you start with Galileo's very small little telescope and go through how things have evolved to the very large modern observatories that are under construction, obviously you can see this, that they're getting bigger and bigger. And so the question that arises is, what drives this need for larger and larger telescopes? And there are two basic concepts here. One is that the bigger telescope is more sensitive. That is because it collects more light. And when the telescope is more sensitive, you can see fainter sources out to further distances in the universe also. The other advantage the bigger telescopes provide is that it has a higher magnification, which is allows the telescope to distinguish between nearby objects or sources in the sky. Technically, we call it resolution. And so if the telescope has a higher resolution, it can resolve sources which are close by in angular separation in the sky. And both these quantities have a dependence on the size of the telescope. The sensitivity, as you can imagine, would depend on the total area that the aperture offers, because that decides how much light it's collecting. So it is proportional to d square, where d is the size of the aperture. The resolution, on the other hand, is inversely proportional to d, which means the bigger aperture allows you to resolve smaller angular distances on the sky. The thing to note is that the resolution also depends on the wavelength of the radiation that is being considered. I will illustrate that with a couple of simple examples. I think most of you will know or would have heard about the Andromeda galaxy. It is one of the nearest galaxies to our own Milky Way galaxy. And if you go out in the dark sky and look at it with the naked eye, you can just about make out a faint blurry patch. If you start looking at it with bigger and bigger optical telescopes, you will see the kind of pictures that I show on the screen here. And as you can see that both the object becomes clearer in the sense that you can make out more detailed structure, which is the resolution. And you can also see that a lot of the objects which are fainter and hard to see in the images made with the smaller telescopes become more clear and more easily seen, and more fainter objects start becoming visible. So this is just an illustration of these two concepts of sensitivity and resolution, which we will have need to come back as we go to the next point. So this is how astronomy started, but you can ask the question that, well, we know that light is waves are just part of a large electromagnetic spectrum, which goes all the way from the lowest frequency or the largest wavelength radio waves to the highest frequency, shortest wavelength gamma rays. And so it's a natural question to ask that can we see the same object in the universe at different wavelengths of the electromagnetic spectrum? And also, do the different wavelengths give us different information about the object? That is, can the studies at different wavelengths be complementary to each other, allowing us to learn more about the object? And third, are there some objects or phenomena which can be studied only at some wavelengths? That means the object may be visible in optical, but not in other wavelengths, and vice versa, that you don't see it in optical, but if you could study it in radio waves, you may see it. And the answer to all of these questions is yes, which is what makes it interesting to ask that how do we go beyond light waves in order to study the universe? And I'll just again illustrate this with an example, which is back to the Andromeda galaxy. So this is similar to the picture I showed a few slides ago, where you can see the Andromeda galaxy in optical wavelengths. And these are images of the Andromeda galaxy made at different wavelengths of the electromagnetic spectrum, going from radio to infrared, visible, ultraviolet to X-rays. And you can see the kind of points that were there on the previous slide, that yes, the object is visible at different wavelengths. And yes, that the object does look different at different wavelengths. Therefore, you are getting some kind of complementary information in the sense that some parts of the object are clearer in optical, some are clearer in ultraviolet and other wavelengths. And if you look carefully, you will see that there are some parts of the object which don't show up at some wavelengths, but show up very strongly at other wavelengths. I'll show this with a couple of other examples. This is an example of what is called the Whirlpool galaxy, M51. And again, you can see it shown here all the way from radio to infrared to optical to ultraviolet to X-rays. And again, the kind of points that were being made which related to the Andromeda galaxy are hold true over here also. Just show this with one more example. This is the very well-known Crab Nebula, which harbors a known pulsar called the Crab pulsar. And once again, you can see that the object looks quite different in different wavelengths, and therefore it is conveying different aspects of the physics of what is happening. And it is interesting that in radio wavelengths, it not only shows you the radio nebula, but if you have the right technique in terms of the instrumentation on the radio telescope, then you can detect the pulses from the spinning neutron star, the pulsar. In some of the talks later today, you will get some aspects of this different views of the universe that are provided from the different wavelengths. What I will come back to is to ask that, what did it take to go from optical astronomy to these other branches of astronomy, for which I've already shown you some results? And as you can imagine, that the first hurdle would have been that how do you get the detectors for detecting these wavelengths? And these obviously came with the technology, because to start with, like I said, we have natural detectors only for optical, but then with technology, man learned how to develop detectors that can detect the different wavelengths. And we'll come to the specific one related to radio in a moment. But there is one other hurdle when it comes to the multi-wavelength astronomy, which is the question that whether these all the different wavelengths can reach us at the surface of the Earth from faraway distant objects in the universe. And this answer is a bit complicated, in the sense that different parts of the Earth's environment, whether it's the atmosphere or the ionosphere, block different wavelengths of the electromagnetic spectrum. And here is a plot which shows this by measuring the quantity called the opacity. So 100% opacity means that that signal is not going to reach us at the surface of the Earth, and close to 0% opacity is what you need in order to be able to study that particular object at that wavelength with ground-based facilities. So as you can see, there are two windows here. One, the optical window that we already talked about, and the other is this large window here, which lies in the radio part of the electromagnetic spectrum, where you should be able to receive radio waves as long as you have the capability for the detection. So you can imagine that the next branch of astronomy that would have grown would be radio astronomy. But like I said, it took a while to be able to understand how to receive and detect radio waves. I won't go into the details of that, except to say that some of the pioneering work for that was done by Acharya J.C. Bose, who first demonstrated generation and reception of radio waves in India back in 1894 in Kolkata. And then came the entire revolution that gave us the radio communication technology. And it is an offshoot of the radio communication technology that radio astronomy was born, because once we had the ability to have detectors that can pick up the electromagnetic wave signal and convert it into electronic signal that we can then process, we were able to then detect radio waves. And this started with Carl Jansky in the Bell Labs, but that's a long story to cover in this short talk. So I will move from there and go to the basics of a radio telescope. How does it work? In principle, the basics is not very different from your favorite satellite dish receiver, in the sense that there is a dish antenna which is parabolic in shape, so that it can bring incoming plane waves from a given direction in the sky to a focus at a focal point. At the focal point, the electromagnetic wave is converted into an electrical voltage signal by a receiving antenna called a feed antenna. That electrical voltage signal is then amplified, filtered, processed, and then finally brought to a detection system, which detects the signal and extracts the quantity of interest. In the case of your favorite satellite dish, it will then process the audio and video signals that are encoded onto the carrier and give you the sound and the picture that you want to see. In the case of the radio waves coming from the distant universe, the big difference is that these signals are much weaker than the signals that we get from our satellite dish system. In fact, they're so much weaker that there's a separate unit that we use, 1 Jansky, 10 to the minus 26 watts per square meter per hertz. And that's a very small amount of power. If you understand electrical engineering, for a typical antenna of 1,000 square meter collecting area and a certain amount of bandwidth, this would be about -100 dBm of power, whereas 0 dBm is 1 milliwatt, and a dB is a log scale, as you will all know. So it's the point I'm trying to make here is that the big challenge in radio astronomy comes to be able to faithfully pick up and detect these signals. A, because they're very weak, and B, when you pick them up with a radio telescope and try to amplify them, there is unwanted noise that gets added because every electronic circuit has some intrinsic noise. And this noise is often much stronger than the strength of this very weak signal that we are trying to pick up. And so one has to build very high quality electronics, which has the minimum amount of intrinsic noise as possible. And sometimes that requires to cool the electronics to very low temperatures so that you can minimize the random thermal motion of carriers, which is one of the main sources of the unwanted noise. But so what happens to overcome these challenges and to achieve high sensitivity, which is, if you remember, the ability to see faint sources, radio astronomers end up using these kind of things. That one, we build very large dishes, several tens of meters or even larger as compared to your small satellite dish antenna. We try to build as high quality, low noise electronics as possible. The other two things that help us, unlike our man-made satellite transmissions, much of the emission coming from natural phenomena in the universe is broadband in nature, which means that the source emits over several, maybe even hundreds of megahertz of bandwidth. So if we can observe over large bandwidths, that is, increase the number of hertz over which we are observing, then we will collect more energy, more flux. And so we try to build receivers which can observe over very large bandwidths, tens to hundreds of megahertz. The other thing that helps is, in order to build up the signal strength vis-a-vis the noise strength, we can observe the sources for a long duration. So again, unlike man-made signals, many of the sources in the universe that we are studying are by and large statistically the same with time. That means if you observe it now, a few minutes later, a few hours later, next day, next year, next century, they would look almost the same, a large number of the sources. There are, of course, sources in the universe which are time varying, and you will hear about some of them in one of the later lectures. But for the kind of sources which are statistically the same, you can observe over a very long duration and integrate the signal. And I don't have time to go into those details, but when you integrate that, it can be shown that the way in which the signal power increases with time and the way in which the noise power increases with time, you can gain in signal to noise ratio by a factor that goes as the square root of the time of the observation. So these are the different techniques whereby we try to achieve the best sensitivity that we can in order to be able to see the very faint sources and get high quality data. So this is a typical example of a large single dish antenna. This is a 100-meter size green bank telescope. It's a fully steerable dish. But as you can imagine, making a 100-meter size antenna that is fully steerable is not an easy task. But even if you make such a 100-meter size antenna and use it for radio astronomy, and let's say you're operating at 300 megahertz of frequency, you will find that this other problem that was driving the large telescopes hits us quite hard. That is the problem of resolution. So the resolution, as you remember, depends also on the wavelength of the radiation. And here at radio wavelengths, we are talking about orders of magnitude larger wavelength than the optical waves. And so a 100-meter size antenna operating at 1 meter wavelength, 300 megahertz frequency, has a resolution of about half a degree, which is 30 arc minutes. 30 arc minutes is the angular size of the moon, also happens to be the angular size subtended by the sun. And so what that means is that with this kind of a telescope, if you were looking at the moon and the moon was emitting radio emission, you would just see one blurred image of this size. Whereas even with the simplest optical telescopes, we know that you can get a much higher resolution picture of the moon where you can make out much more finer detail. So this is a challenge for radio astronomy in the sense that the resolution requires even much larger telescopes to be built, and it's not practical to build very large single dishes of more than a few hundred meters in size, and so this problem took a while to be resolved, but it did happen when it was realized that by Sir Martin Ryle, who actually got a Nobel Prize for this discovery, that in order to synthesize a much larger telescope as far as the resolution is concerned, you can build a large number of smaller antennas and spread them out over a distance, which is the size of the single antenna that you would have liked to build. So, for example, you can see this array of antennas here called the Very Large Array Telescope in the US, which has got multiple smaller antennas. Each are still of the order of a few tens of meters in diameter, but they are spread out over a distance which is now of the order of 10 kilometers or more. And what was shown is that if you can combine the signals from all of these antennas and bring them together and do the right kind of signal processing, then you can actually synthesize an image of the source that you're studying, which would have a resolution which corresponds to replacing the D, which was the size of the aperture of the telescope, by the largest separation of the antennas in the array. So this now allows you to get much higher resolutions with radio astronomy antennas by using arrays of antennas spread out over large distances. But each of them can now be relatively modest in size. So this allowed radio astronomy to again be competitive in terms of providing you complementary resolution to, say, an optical telescope for being able to study the universe with greater detail. And so today, most of the radio astronomy antennas observatories that are built are by and large array telescopes of this kind. And I will illustrate that now by we're talking about a typical modern radio telescope like our own GMRT, which is a low frequency facility. So what that means is that I showed you the radio window over which you can observe with ground-based radio telescopes, which is very large in its frequency coverage. It goes from about 30 megahertz to about 300 gigahertz. And no single radio telescope can really cover that wide range of frequencies for various technical reasons. And so usually the radio telescopes are built to focus on some part or the other of that radio window. And so in our case, our focus is towards the lower frequency part of the radio window, going from about 100 megahertz to about 1450 megahertz. And in this range, the GMRT is one of the largest and most sensitive radio facilities in the world. As I said, it's an array telescope, 30 antennas of 45-meter diameter each, spread out over a 30-kilometer region, and I'll show you that in a moment. It's completely designed and built in India during the 1990s, led by the team that Professor Govind Swarup set up, and operated since 2002 as an international facility, and recently upgraded during the period about 2013 to 18, and released around 2019 as a updated and vastly improved facility. So this is where it is located. So if you travel from Pune to Nasik, you will cut right through the GMRT array. The 12 antennas is located in a central 1 kilometer by 1 kilometer compact region, and the remaining 18 spread out in this roughly Y-shaped structure, stretching out to a little bit over 14 kilometers. So therefore, that largest, the total area that you're synthesizing is the equivalent of close to a 30-kilometer size antenna using this. And The GMRT, if you look at it in the Google map, you can actually see the individual antennas. This is that 1 kilometer by 1 kilometer central square. You can make out some of the individual antennas here. This is a view of the same central square antennas taken from a nearby hill. This is a close-up of one of those. So now you can see 45 meter is still quite a large antenna. And as I mentioned, the electromagnetic waves that are brought to a focus here, they are picked up by a small feed antenna. So you can see the kinds of feed antennas used at the GMRT, which convert to electrical signal, and the most sensitive amplifiers and electronics is located right at the top of the focus. And you need this special kind of crane to reach to the top over there. You can also see that the antenna looks more like almost transparent, and you wonder how does it reflect the radio waves. And it's actually not transparent. There's a fine wire mesh which acts as a reflecting surface, and the wire mesh is sufficient to reflect the radio waves of the wavelength of interest here fairly efficiently, which would need to be replaced by a solid surface if you were to be operating at higher frequencies or shorter wavelengths. So that's one of the unique designs of the GMRT, which makes the antenna much lighter in weight and therefore cheaper and easier to build. In order to make any of this kind of telescope like the GMRT fully functional, I just want to point out that there are several aspects of engineering and technology that are involved. And you could have seen that just to build large antennas of this kind requires very good expertise in mechanical engineering. And then to position and move these large antennas accurately requires a very good quality servo system. And then, of course, all the RF electronics from the antenna feeds to the low noise electronics and the entire receiver chain, which brings the signal down from the top to the bottom. And then the signal is transmitted via optical fiber from each of the antenna sites to the central building at the GMRT. So a lot of optical fiber technology. And then in the receiver room, it's converted back to electrical signal and then digitized, and a lot of the signal processing that is required in order to combine the signals from all the 30 antennas is done using sophisticated digital signal processing. And then there is the entire telemetry and motor control system to control all of these 30 antennas spread out over large distances and make the whole thing work in a coordinated manner as an observatory. So all of that requires a lot of hardware and software systems. And then finally, the data that you get in order to analyze it and make sense of it and extract the astrophysical properties of interest from the source requires a lot of offline data processing. And so there is a large number of engineering techniques that go into any such large observatory. And this was actually, in the case of the GMRT, I just want to point out that this is something that was recognized by the IEEE, and the GMRT was awarded an IEEE milestone just about a bit over a year ago for the pioneering contributions that the GMRT made, both to the techniques and technology for radio telescopes, as well as for the kind of science and results that it has produced over the years. And the GMRT is used by astronomers from all over the world. And I just show a quick snapshot here. And it's a highly competitive facility in the sense that there is a very high demand from astronomers from all over the world. And it's usually a competition for getting the best proposals that get accepted for scheduling and getting time on the GMRT telescope. And so just in a nutshell, the GMRT, which was built in the 1990s and inaugurated on 4th October 2001, completed 20 years of operation last year, 4th October 2021. And we had the privilege of having Shri Ratan Tata, who did the honors to inaugurate the facility, to join us at the 20th landmark occasion. And it was a good moment to review many of the interesting science results of the GMRT and also talk about the future possibilities for the growth of the telescope. I will now move and talk briefly, just realizing that I may probably be running out of time, about the next generation international facilities for the future. And there are quite a few that are coming up in different wavelengths. You may get to hear about some of the other wavelengths in other talks, but what I want to focus on is the square kilometer array, where again, India is a participant in this project. So the square kilometer array is a next generation facility, and it's just interesting to compare it with the GMRT. So GMRT is, though it's an international facility, it is a national level facility in the sense that it was built by a single country like India. At the international facility now, if you want to build something which is 5 to 10 times more powerful or better than a facility like the GMRT, a single country cannot really afford to do that. And so what happens nowadays is that different countries come together to pool together their resources, both the technical resources, knowledge and the understanding of how to build things, as well as financial resources in terms of funding that their governments can provide, and try to pool that together and then plan and design and build the next generation facilities. So a square kilometer array is, in that sense, next generation radio astronomy observatory that is just completed the design phase and is entering the construction, which is just got launched and will go on for the next 7 to 8 years before it is fully operational.
So Professor Gupta, sorry to disturb you.
Yes.
If you can close it by 5 minutes from
Yes.
now,
Yeah.
then we'll go to question and answer session.
Yes, and so the phase 1 of the SKA itself will be much bigger than GMRT. So GMRT is 30 antennas. There are 200 antennas planned in that first phase, spread out over much larger distances, and it will be located in Australia and South Africa. And there is already more than 10 countries in this global cooperation, where we are one of the partners. So this is what the SKA antennas will look like in South Africa. Again, here there are dishes, but the SKA antennas in Australia for the low frequency part are actually going to be dipole antennas, which are in stations where the signals from the dipole antennas are combined in order to make it look like one large dish antenna equivalent, but with more capabilities. And then many such stations are there in the array. This is just a snapshot of the international participation in the SKA, different member countries who are either joined or planning to join. This is just to give you the sense that in terms of the technologies, as I mentioned when talking about GMRT, the different areas of technology, the SKA is such that it is pushing many of these technologies to the next much higher level. I won't go into the details of this, but whether it is the design of the low noise electronics, or it is the total data flow over the entire array, or the requirements to process the data, the computing challenges, and how to store the data and manage it, all of these are truly at the cutting edge in terms of what is required in order to make all this happen. And so this is just one example of the storage requirements for the SKA compared to some of the major databases or storage facilities in the world. Just very briefly to mention that India is an active part of being in the design phase of the SKA, and during construction phase, we are looking at some specific contributions in the SKA project. In addition, of course, the Indian astronomers are gearing up for being able to use the SKA when it is released for observations. And there are lots of science interests and goals that are being discussed by the science communities in the country. So I'll stop here. I mean, I added this just because there are a lot of students who are listening, but I don't know if there is enough time. We can take it up if there is a discussion. So Chiranjeev, you can tell me how you want to do this.
Yeah, you can. We can go for question answer now.
Yeah, let's do that. And if there's specific questions from students about career tracks, then we can talk about it.
Okay. So someone, Gauri Ajampura, is asking what materials are used to build low noise electricals.
What materials are used to build low noise
Low
electronics?
noise he has written electricals, but it may be electronics.
Yeah. So, building low noise electronics is a very specialized skill. When you talk about materials, I mean, the materials are the same materials with which you build normal electronics. It's just that the way you design the electronic circuits and the way you build them, it is done so that the noise introduced intrinsically by the electronics is minimized. And the further thing there is that in many of these cases, we cool the electronics to lower temperatures so that again, the amount of random noise generated is reduced.
Okay. So now another next question is that he's saying, sir, I worked in X-ray pulsars for my master's thesis. My question is, if anyone wants to work with radio pulsars, is there any platform like HISA, HEA-SARE, where can we access radio telescope data for pulsars publicly for timing and spectral analysis?
Okay, I think you're mentioning some platform for accessing pulsar data. Is that the question?
Yeah, platform like HEA-SARE, if you are aware of. Capitalized HEA-SARE.
Okay, so I think I'll just answer this from the point of view of radio pulsar data and observations.
Yeah.
Mostly the radio pulsar data, because of the fact that the data is very high volume when recorded at the observatory, is generally available with the people who have made the proposals for those observations. There is not too much of pulsar data that is radio pulsar data that is publicly available. Some reduced data sets are available publicly for certain kinds of things, but they are of limited nature. Usually it is, you have to be part of some research group in order to have access to the level of pulsar data that you may need for carrying out research in that area. I'm not sure if I've addressed the question the way the person has asked it, but they can get in touch with me or any of the colleagues working in radio pulsars if they want further information, or if they want to join some of the projects where we are working with radio data for pulsars.
Yes. Okay, so now next question is Isika is asking, sir, I am interested in pursuing career in astronomy and astrophysics.
Yeah.
If you have something to guide her.
Okay, I mean, so I'll just put my slides here, that this is what I have to say if you want to have a career in astronomy and astrophysics. And the basic track is what I call track 1, where you go through a regular, physics education, BSc, MSc, PhD, and become a researcher. There is a couple of other tracks. What I call track 2 is for people who are more interested in instrumentation and experiments and have done, say, a degree in engineering rather than a degree in physics. Then also there are avenues because there are a lot of these interdisciplinary areas where engineering knowledge, instrumentation, and techniques is applied in astrophysics, and several current astronomy research people, including myself, have come through this kind of a track. And you can then become a faculty member and a researcher with emphasis on maybe more on instrumentation and less on astrophysics, but it depends on how you evolve. There is the third track, which I put there, which is for people who are not interested in really doing research, but like astronomy, want to work with hands-on on instrumentations and techniques. Then there are positions in observatories where you can work as part of the engineering staff, engineering team, carrying out development of instrumentation, which you may or may not use for research yourself. So this just in a nutshell. Again, I don't know if this is sufficient to address the question that the person is asking, but again, they can get in touch with any of us working astronomers and can get further guidance.
So the next question is, Vice is asking, how sensitive are these telescopes? So I would request you if you can give him some number or something like that, because he's asking how sensitive are these telescopes.
Which telescopes? You mean, okay,
he's referring to radio telescopes,
radio, okay.
SCA maybe, or
I will,
with WRPA.
yeah, so I will give you some examples. So I gave you this unit 1 Jansky, 10 to the minus 26 watts per square meter per hertz. So when we look at radio sources, we characterize their flux in the units of Janskys. And then you can ask, what is the weakest source that we can detect? And so some of the weakest sources that a telescope like the GMRT can detect are a few micro Janskys in strength. Okay, so I mean that I can only give you a relative sort of answer because you know how sensitive a telescope is just in units of the flux that it can detect. Again, you know, I hope that answers the kind of question the person is asking. Yeah. You can of course translate that to what kind of objects can be detected, but that depends, you know, where the object is, how far away, and so on. But the thing to remember, so some of the strongest sources in the sky that we see are of the order of 1,000 Janskys, and the most sensitive radio telescopes of today can detect sources which are of the order of micro Janskys in strength.
Okay, so now last question I will ask. Somebody is asking, can we pursue astronomy and astrophysics in middle school? If we can, then where?
Middle school. So here's my last part. I hope your middle school has this. Okay, if your middle school has an astronomy club, that's the place to start.
Okay, so there are lots of questions, but we cannot go asking so many questions. I'm sorry to the participants. Maybe
so this is Dr. Porida this side. So
yeah.
we have a whole bunch of students sitting here.
So they want to ask some questions. So please carry on.
Yes. One question is coming from, what is your name? You can tell your name and ask the question here.
So this is, they are sitting here actually.
Good afternoon, sir. My name is Mitorshi. Sir, my question was like, what is the scope of getting internships and like for like GMRT and other like areas like this? How can we like pursue for internships in our undergraduate level?
Yeah, so there is quite a bit of scope for internships in any one of these observatories or institutions in the country. For example, we take interns who are undergraduate students while they are doing their degree. And the best way to do is to, so there are two kinds of things. One is there is a formal school. For example, there is a radio astronomy winter school that is conducted, which is just a very short of the order of 10 days to 14 days. And Professor Saikia is not on, I think, right now, but he's the one who's been organizing it from the Ayuka side. And we have faculty members from NCRA who jointly organize this. That's a good place to start if you are an undergraduate. You can always approach faculty members in these institutions to ask for internship in the summer. Often there's a good number of students that we take in what is called the summer training program that goes through some selection process. There are different options. Some students like to work more on theoretical things. Some students like to work more on experimental things. So both kinds of possibilities are there.
Okay, sir. Thank you, sir.
Is there anybody from this side? Dr. Porida? You are muted.
Hello, Dr. Konar.
Yes.
May I ask a question?
Yeah, sure. Carry on.
Yeah, okay. Professor Gupta. Hello.
Yes,
Am I
hello.
audible?
Yes.
Yes, okay. My question is how we decide that a telescope can be used for molecular lines or not?
How do we decide? So it depends on what frequency you are expecting that line to be.
Molecular lines are generally known.
Yeah. And so if you know the frequency at which the line is, then if the telescope has coverage in that frequency, then then the next question to ask is how strong or weak do you expect that line to be? And then that's a matter of whether the telescope has the sensitivity to be able to detect that line. Maybe after a long integration of the data, it may be able to detect it. But the first thing is, of course, that the frequency has to match.
Okay. Thank you. Okay, Dr. Kunal.
Okay, so let's thank Professor Yasant Gupta for a wonderful talk. And it's our pleasure, really. We are very happy with you that you have given us your priceless time. Now we'll go over to the next talk. Our next speaker is Professor Patrick Dasgupta. And the title of his talk is First Radio Burst, the Enigma of Extragalactic Lighting Flashes in Radio. And Professor Patrick Dasgupta will be introduced by Dr. Gautam Singh.
Okay, thank you so much, Kunal sir. So very good afternoon to one and all present in the meeting. It's my great privilege to introduce eminent professor and researcher, Dr. Patrick Dasgupta, to you all. Dr. Gupta is presently working as a full professor at Department of Physics and Astrophysics, University of Delhi. He has done integrated MSc from BITS Pilani in the year 1981, and then PhD in physics from TIFR Mumbai in the year 1988. After completing his PhD from TIFR, he has done his postdoc from IUCAA Pune with twice postdoctoral fellowship. Just after finishing his postdoc, he joined as a faculty at Department of Physics, University of Delhi, and since then he is working over there. His research interests include radio galaxies and non-evolving luminosity functions, quasar redshift periodicities, gamma ray burst sources, protective measurements in quantum mechanics, bound probability, black holes, Dirac equation, magnetic charge in the local duality symmetry, Bose-Einstein condensates in hexagonal lattice, and nonlinear Dirac equation, gravitational waves and astrophysical sources, dark matter, black holes, and fast radio bursts. He has supervised many PhD and master students. He has 47 research publications in internationally reputed journals and 14 popular science articles in his credit. He has delivered more than 68 invited lectures, both in offline and online modes, in various institutions in India and abroad. He also has many awards, fellowships, and membership in his credit at national and international levels. With these words, I would like to invite Professor Patrick Dasgupta, sir, to deliver his lecture. It's over to you, sir. Thank you.
Thank you very much, Professor Singh, for the kind introduction. And I will straight away go for the talk. Let me try to share the screen.
Patrick Dasgupta, I welcome you.
Thank you, Professor Suresh.
Yeah, I welcome you.
Great
I am
to be
thankful here. Nice to see you after a long time.
Share the screen.
The same to you, Professor Dasgupta. This is Chiranjeev.
Nice to see you, Professor Chiranjeev. Yeah. Are you able to?
Yes, we can see you.
Your slide is visible.
Screen.
I think internet has some trouble. The sound is.
Yeah. Shall I try to increase the size?
Can you make it full screen? Is it possible to make it full screen?
Yeah, let me try to do that. Let me try to do that. One moment. Huh?
Yes, please.
I was sharing a different. Sorry, I wanted it to screen because on neutrino, try to share that screen.
Yes, we can see.
Sorry, the presentation has already started?
Yes, it has started, but this speaker is facing some technical problem.
Okay. So that's why students are curious to know there is
Yeah.
no voice.
No, it has
Okay.
started because of the technical problem.
Okay, fine.
Okay, am I audible now?
Yes, you are audible.
And are you able to see the screen?
Not yet.
Oh, I see.
Please share it. If it already say unshare and then share it.
Oh, I have to do that. Okay.
If it doesn't work, then we do generally like this.
Are you able to see
Yes,
the slide?
yes.
Great. Yeah.
Great. Yeah.
So thank you for having me for this workshop. What I will try to do is just give basic introduction to fast radio bursts. This is comparatively a recent field in the field of radio astrophysics and radio astronomy. And Professor Yashwant Gupta gave an excellent lecture introducing the basics of radio astronomy and my job has become simpler. Okay, so the birth of, am I audible?
I think to me,
Sound is not clear.
there is a signal delay and not so clear. Maybe
sound is not clear.
Yes, sound is not clear and delayed.
Now, am I audible now?
Yes, now yes.
You are audible.
All right. I see. I see. Yeah, it's a big problem from.
You are connecting
Oh,
from phone?
thank you. Thank you. All right. So the birth of this started at 20 when accidentally team, while doing a search in archival data, they suddenly noticed a lone peak.
No, sound is not clear again.
First
Sound is problem.
show the lone had dissembled a pulsar peak. Oh, sound is a problem, is it?
Yes.
Are you able to hear me now?
I can hear you very well, but when you are giving the lecture, it is showing that it is stretching the words. Maybe signal problem.
Oh. Yeah, there's a signal problem. Are you able to hear continuously now?
But it is looking that somewhere it is being delayed.
It is very strange that
Some problem is in the software.
Strange.
So sorry, Professor Dasgupta. So I think there is some network issue. So you may try to maybe switch other networks. Maybe it will work.
Yes, we don't hear anything.
Yeah, now he left the meeting actually.
Maybe some other Wi-Fi network or something like that.
You are not clearly audible. Not clearly audible. Your voice is delayed and is getting broken.
I'll tell you what, given this limitation, it is better that I simply answer, because there is some problem with the suggest is that students participate, they can ask any questions.
Okay.
So Kunal sir, how should we go about it?
Yeah, so students, participants.
Dr. Chiranjeev?
Yes.
Am I audible?
Yes, you are audible.
Can we have some alternate arrangements? Can you request sir to send you the PPT, what you shared it from here? And
But we are not hearing him at all. That's the problem.
you can contact him over phone so that we can have the PPT being shared and the audio can be managed with a low bandwidth. Low bandwidth is a problem when the video is being shared. We can switch off the
Okay,
video.
then we can do that.
It will take hardly a few minutes through mail.
A few minutes. Right.
Just
let me talk to him.
Yeah.
Let me talk to him. He is unable to take the call. It is saying that the person is unable to take the call. Let me message him in WhatsApp. So he may be trying to do something, that is why not accepting the call. So can we do one thing? We can go to the next speaker if he is available, and then come back to Professor Patrick Dasgupta in the next. That is one option.
Yeah, but we can have 1 or 2 minutes.
Sorry. Sorry. So yes, can you tell what do you think?
I think for that we may need the permission from Professor Patrick Dasgupta that we are going ahead with the next speaker. So just have a small talk that we are shifting the.
Let me drop the.
And in the meanwhile, you can arrange the PPT and or delivered audio through your mobile phone. You can put it on speaker mode, and that can be managed from your end. But for that case, we would like to have a word from Professor Dasgupta himself.
Okay, so let me
just have 1 or 2 minutes. You can wait.
Chiranjeev, call him on WhatsApp.
Okay.
Chiranjeev, call him on WhatsApp. He seems to be online.
Okay. Let me. Okay, so Professor Dasgupta himself said that start the talk with Professor Dipankar Bhattacharya, and in the meanwhile, he will try to fix.
So it can be taken later on. Second. Dr. Konar, वो शुरू करा देते दूसरा.
हाँ, Professor Bhattacharya, are you there?
Bhattacharya सबका करा देते शुरू.
Yes, I'm there. Give me a minute to invest if I have to get ready. Because I was waiting for.
So let us start the introducing, etc. And meanwhile, you just fix your PPT, etc.
Yes.
Okay, so because of the technical problem, we couldn't do Professor Patrick Dasgupta's talk. Now we will go to the next speaker. The next speaker is Professor Dipankar Bhattacharya, and the title of his talk is Cosmic Explosions. And Professor Bhattacharya will be introduced by Dr. Gautam Singh. Dr. Singh, please.
Okay, thank you, Kunal sir. So hello everyone. It's my great privilege to introduce eminent speaker Professor Dipankar Bhattacharya to you all. Dr. Bhattacharya is currently working as a Sunanda and Santi Mein Basu Chair Professor at Department of Astrophysics, Asoka University, Sonipat, and Distinguished Professor at IUCAA Pune. He has completed his MSc in Physics from Jadavpur University, Kolkata, West Bengal, and then PhD in Physics from ISC Bangalore. After PhD, he did his postdoc from University of Amsterdam, Netherlands, and was also a visiting fellow at Institute of Theoretical Physics, University of California, Santa Barbara, USA, in 1991. Just after doing his postdoc, he joined Raman Research Institute, Bangalore, as a scientist and promoted to full professor in the year 2004. In the year 2007, he moved to IUCAA Pune as a senior professor and remained there till 2017. And he has also held many administrative positions during his career so far. His research interests include high energy astrophysics, such as compact stars, white dwarf, neutron stars, black holes, magnetic fields in compact objects, and accretion flows, cosmic explosions, diffuse gas, stellar wind bubbles, photoionized medium, radio recombination lines, and radio optical X-ray astronomy, coded mask imaging. He has supervised 19 PhD theses and 40 master undergraduate theses, 30 summer projects, and 15 scientific training. He has published more than 180 research papers in SCI index journals. He has also been awarded with many fellowships and memberships of societies at national and international levels. With these words, I would like to invite Professor Bhattacharya sir to deliver his lecture. It's over to you, sir. Thank you so much.
We are very happy to have you, Professor Bhattacharya.
Thank you so much. I think this was more than generous introduction. You have really been very diligent in finding all the information that is possible.
Welcome, Bhattacharya. Welcome.
Thank you very much. So it's a great pleasure for me to be at this workshop, and many thanks to the organizers for asking me to do this. And really a great opportunity to interact with such a large number of students, which is always a pleasure. And it's my first interaction with you at Amity University. And since now I am located not very far from you,
Yes.
I hope that we'll be able to visit your campus someday and then interact with you in person.
Definitely, we want long association with you.
Thank you very much, and I look forward to that too. So let me then share my screen.
Right.
Let's see. So,
Is it visible to you, the share button?
yeah.
Okay. It is activated.
So I think I'll share the desktop itself.
Yes, visible.
It is visible.
So you can see my presentation, right?
Right. You can see.
Okay. I will finish this up. Okay. So let's get started. So the reason I chose to talk about this area is because this is, as the title suggests, a talk about cosmic explosions. But the study of this area is exploding right now. So we have many new instruments, new methods of studying explosions and so on. And over the next decade, this is going to be a very major endeavor of, I think, almost every astronomy institution. And that's simply because all the future major instruments are going to produce a wealth of information about cosmic explosions. They're already beginning to do so, but much more powerful instruments are in the offing. For example, the Rubin Observatory, already the Gaia satellite is providing a lot of information. Square kilometer array, the Professor Yashwant Gupta talked about, and various other space-based observatories. So we are in for a very major growth in this area. And I thought maybe I'll introduce this area to our young students. And by the time they're ready to enter astrophysical exploration, this is something that they should look forward to. So let's start. So the universe consists of many objects. Now, if you look up in the sky at night and look up tomorrow, look up the day after, the sky looks more or less similar. But what we don't easily see with our naked eyes are objects, many objects, which change their brightness in very short time scale. And this happens not just at optical wavelengths, but over the entire electromagnetic band. And many such highly variable objects are actually explosions going off somewhere or other in the universe. So there are many objects that display explosive phenomena. So in astronomy, you often call them transients. And in recent times, major strides have been made, as I mentioned, in the study of such events. And there is a whole branch that has now developed, which is called time domain astronomy, which is spending its efforts in this direction. If you look at the major telescopes, their data and so on, many such events are visible every day, spanning the entire electromagnetic band, and the new band that has become an exciting new sub-branch of astronomy, and that is gravitational waves. So all of these explore this explosive phenomena in many different details. So there are many types of this explosive events that we come across. Very close to home, we have solar flares. There are explosions going off on the sun quite often. And many sun-like stars also show these flares. The solar or stellar flares is one class of explosions that we encounter. Then there are nova explosions, supernovae, X-ray bursts, fast radio bursts. I was hoping that Patrick could cover this in his talk, but hopefully he'll do so right after this talk. Flares from magnetars, kilonovae, gamma ray bursts, merger events of compact objects producing a lot of gravitational waves, and many others yet to be discovered. And while the explosions is what we're going to talk about, the aftermath of the explosion is also important, and they are also visible in many cases. So let's go through a sort of overall broad brush summary of our knowledge in this area in this talk. But before I get into explosions, I want to say something about the most common sites of these explosions. And these most common sites happen to be compact stars. Now we all know and we can see stars in the sky. They emit bright light, and we classify them as normal stars. So what is happening in normal stars is that normal stars like the sun, so some of the stars that you will see in the sky are less massive than the sun, some are much more massive than the sun, but all of them are in a state where they are basically gaseous objects and they're very hot. And it is the heat that is within the star that causes a large amount of thermal pressure. And this thermal pressure is holding the star up against its own gravity. Now let's make an analogy with the Earth. So we are standing on the Earth. So Earth is made up of some material. We are attracted by the Earth's gravity, but every piece of material that Earth is made up of is also attracted by that gravity, which is self-gravity. So if there was nothing to stop compression of the Earth under this gravitational force, the Earth would simply shrink and become a point. So there is a pressure in this case of the Earth. This is the pressure comes from electrostatic repulsion between charged particles, like the electrons and electrons, protons and protons. So which gives us the solid state forces which hold up the Earth against gravity. In case of stars, this pressure comes from just the pressure of hot gas. However, when you have something hot like the star embedded in surrounding space, which is empty, then heat has the habit of leaking out. It leaks out in the form of radiation. And this is precisely the radiation that we see from all these stars. They look bright because radiation is leaking out from the stars. And as the radiation leaks out, it carries away the heat energy that is present within the star. So if there was nothing to replenish that energy, then because of the heat leak, the star would continue to contract due to the gravity. The reason why we see the sun basically stable in its current state for billions of years is because this heat that is escaping the surface in the form of radiation is regularly replenished by nuclear fusion that is undergoing at the center of the sun or at the center of any of these stars. So basically, normal stars are in equilibrium because thermal pressure opposes gravity, and this thermal pressure is kept up by nuclear fusion at the center. However, nuclear fusion means that you need nuclear fuel. In case of the sun, it is the hydrogen that is being converted into helium, and the hydrogen at the core is getting used up. So once all of it gets used up, nuclear fusion will stop and gravity will then win again. So it will try to make it more and more compact. So at the end of the evolution of normal stars, we will always have the center of the star where nuclear burning has exhausted. And gravity wins and makes that central region more and more and more compact. So at the end of it, what we're left with are objects which we call compact stars. And these compact stars can come in certain varieties, but the common property is that they are very dense. They're formed as end products of stellar evolution, and because gravity wins, it compresses this material to very high density, and they are very dense. And again, these compact stars, at least the stars which still are able to resist gravity, matter there is degenerate. Now, this is a concept which we don't often come across in our everyday vocabulary, but this is actually present in many solid state materials. In condensed matter physics, people would be aware of this. So in degenerate matter, what happens is that because particles like electrons, protons, they obey something called Pauli's exclusion principle. When you condense them to a small volume, they have to occupy momentum states of different value. So they end up occupying momentum states of high value, as well as all the lower momentum states which get completely filled. So because of that high momentum, it produces a pressure, which is a quantum mechanical pressure. And this degenerate matter giving you quantum mechanical pressure is part of the reason why these stars are held against gravity once they become very dense. The higher the density, the higher is the pressure of degenerate matter. So there are stars which get supported by the degeneracy pressure of electrons. We call them white dwarfs. White dwarf radii are roughly like the radii of the Earth, but masses are of the order of the mass of the Sun. So basically, you take the Sun, compress it to the size of the Earth, you would get a white dwarf. But the electron degeneracy pressure is strong, but strong up to a certain extent. If you keep on piling more matter onto top of a white dwarf, at some point it will give away. And it gives away when the mass limit of 1.4 solar mass is reached. And this is a number which was first worked out by S. Chandrasekhar, and it goes by the name of Chandrasekhar limit. So once the white dwarf acquires a mass, if you keep on adding mass to it, if it goes to 1.4 solar mass, then electron degeneracy pressure can no longer support gravity anymore, and they will collapse and form maybe an even more dense object. So what even more dense object can exist? If you take a white dwarf material and then keep on compressing it even further, then at some point, electrons and protons, which are present in white dwarfs, will start combining and start making neutrons. And the fraction of neutrons in such material will keep growing, and there will a point will come where the degeneracy pressure of these neutrons plus the short distance repulsion between these neutrons will provide sufficient pressure to halt the collapse against gravity. The stars which have attained that state are called neutron stars. These neutron stars are even more dense, so it is like the mass of the Sun squeezed into a radius of about 10 kilometers, which is really compact. However, these neutron stars also have an upper mass limit. Beyond a point, even these pressures, neutron pressures, cannot hold up against gravity anymore. And if you happen to have a compact object with a mass larger than that, there is no escape against gravity anymore. The star will collapse and form a black hole. So the objects that we will refer to as compact stars for the purpose of this particular lecture are neutron stars and white dwarfs. And you can imagine that the gravity at the surface of neutron stars is much stronger than the gravity at the surface of white dwarfs. And gravity at the surface of white dwarfs is much, much stronger than what we are used to on the surface of the Earth. Okay, so with this preamble, let's now take a look at how objects like these become a rich source of explosive phenomena. So what powers an explosion? Now, any physical system can be assigned a mechanical response time, which let's call it dynamic time, TDYN, as I have written here. For an object which is held by gravity, this dynamic time is given by square root of the local size of the object divided by the gravitational acceleration. You would be familiar with this if you have taken a simple pendulum and oscillated it. Its dynamical time is given by square root of L by G. And when you take on the whole object, let's take the entire Earth, the dynamical time scale can be rewritten, this expression can be rewritten as 1 by square root of the Newton's gravitational constant times the average density. And this goes for any object held by gravity. So given an object, if you have a little matter on the surface of the object, you would apply an expression like that to evaluate your dynamical time. Or if you consider the whole object, you would use that to evaluate your dynamical time. So you can assign a dynamical time to this object. Now, any piece of material or the entire object itself is bound by gravity with a total binding energy. Now, somehow, if you are able to produce and dump in this system an energy E, which is much larger than this binding energy, in a time which is short compared to the dynamical time, then the system responds explosively. Now, it is possible for us to dump this energy slowly, much longer over the dynamical time, much longer than the dynamical time. Then what will happen is, as you dump energy, the system will adjust itself and you'll have a quasi-static response, a slow effect on the system. And some of this energy will also get radiated away. However, if you dump the energy too quickly, then the system does not have any way of mechanically responding to it within the time that you are creating the energy. And then it has to respond to that entire energy in one dynamical time scale. And that energy being much larger than the energy that is binding it together, the system explodes. So the requirement is then to release a large amount of energy over a very short time. And this kind of event happens, for example, in thermonuclear fusion, gravitational collapse, or collision of objects, or merger of objects, and also in magnetic unwinding or reconnection. So we will see some examples of it. So let's start with a discussion of magnetic power. Solar flare, which I mentioned in the beginning, is one example of such magnetic power. So you have magnetic power released, which throws out material from the solar surface. Energy is up to about 10 to the power of 25 joules are deposited within a small amount of material in minutes. Now, just to put these numbers in perspective, 10 to the power of 25 joules is 10 billion times the power of the energy of the atomic bomb that was exploded in Hiroshima. 10 billion atomic bombs. So each such event has energies of that scale, and during solar maximum, several such events occur per day. So you can imagine how much energy is being released. And when you go to compact stars, there are neutron stars which have very, very strong magnetic field, and subsurface magnetic field is tangled, and energy is free energy is available there, and surface can crack, and some of this magnetic energy can get released in a very short time scale, short bursts. For example, there are something called magnetar hyperflares which release about 10 to the power of 39 joules within a fraction of a second. Now you can see, now going from 10 billion atomic bombs, we have gone 14 orders of magnitude higher over here. So you can then place this in context as to how energetic these events are. And that's why these things explode. A part of the surface would explode, or the magnetosphere, which is sitting right above the neutron star, will show explosive characteristics. And powered by similar events, probably smaller events, there would be material, let us say electrons and protons, or electron positron plasma, which will be ejected from the star. It can interact with previous such ejected material, and that collision can then generate fast moving electrons, and there's magnetic field there, and these electrons moving in this magnetic field can produce wavelengths of all kinds, including radio waves. So you can get bursts of radio waves, and this is one possible way that fast radio bursts are produced. So fast radio bursts are thought to be a member of this class of objects. So I'm not going to talk much about fast radio bursts because you will hear from Patrick, I hope, in more detail about it. But fast radio bursts seem to release energies up to order of 10 to the power of 35 joules in less than a few milliseconds. So this is all powered by magnetic fields. So how do magnetic fields manage to create such havoc? So just to give a brief idea. What happens is that you have a mixture of plasma and magnetic field in all these objects. Material is in plasma state, which means it's fully ionized. You have ions and electrons moving about. Now, currents flowing through this plasma, let's call that current J, they create the magnetic field. Now, once the magnetic field is created, the magnetic field acts back on the charged particles carrying these currents. Charged particles moving cause magnetic currents, and magnetic field always generates forces on moving charged particles. So this quantity, which is a vector cross product of current and magnetic field, is a measure of the Lorentz force that is created per unit volume in this environment. So if you build up magnetic energy in a confined space, this force also builds up. And at some point, you can get an explosive release of this energy because of the strong forces that can build up as the magnetic field builds up. So twisted and tangled magnetic fields contain more energy than simpler magnetic fields. So twisted and tangled magnetic fields, if you generate them, over time they tend to straighten out and release that energy. Further, in this material, if there are regions of magnetic field line reversal, so there is magnetic field line, one field line going this way, another field line going that way, then those regions can come together, collapse, and release a lot of energy. That is called reconnection. So in sun-like stars, what happens is that rotation and convection in outer layers builds this magnetic energy by a dynamo process. So here is a animation of how such dynamo process works. So you can see that over time magnetic energy builds and magnetic field lines get denser and magnetic energy gets piled up subsurface. And at some point, this magnetic fields erupt and material is thrown out. And oppositely going fields reconnect and you get a solar flare as the material is thrown out from that region like this. A similar thing happens in magnetars where there is pre-existing magnetic field, but there is a tangled state subsurface, and this tangled magnetic field over time tries to straighten out, crack the crust, and generate magnetically powered bursts. Coming now to nuclear power, that is the second source of explosive energy I mentioned. So nuclear power is primarily thermonuclear fusion that we are talking about. We have two nuclei. So nuclei are positively charged. Let's say even protons, that is the first stage of nuclear fusion, hydrogen burning to helium. So protons come together. But the protons to come together, they have to overcome the repulsion between them because of the positive charges. Once they do so, and once they come very close together, they can combine. In case of hydrogen, you have proton combining to deuterium and deuterium combining to helium, giving rise to a lower binding energy state. So therefore, you get the rest of the energy to be released. So you get a so that energy that is released, it gives rise to a explosion in certain circumstances. And what are those circumstances? So to understand that, let us take into account the fact that for these two to come together, they have to overcome this Coulomb repulsion. So the Coulomb repulsion creates an energy barrier, and a quantum mechanical tunneling has to happen for these to come together and for fusion to occur. And this quantum mechanical tunneling is an extremely sensitive function of energy. And since energy here comes from thermal energy, so it becomes an extremely sensitive function of temperature. So the reaction rate is a strong function of temperature. For example, hydrogen burning has a dependence of temperature to the power of 6, helium burning has a dependence of temperature to the power of 40. So a slight difference in temperature can change the rate of energy production by an enormous amount. And now, if this ignition happens in a state where the material is degenerate, that is perfect for generating explosions, because if the material is degenerate, you change your temperature, but the pressure doesn't change. So therefore, material remains in the same density state, and the energy production continues to increase. So that can become highly explosive. And it's called a runaway reaction. So how much energy is generated? In hydrogen burning, about 0.7% of the rest mass gets converted to energy. In helium burning, 0.07%. In carbon oxygen burning, it's about 0.03% of rest mass which is converted. Now, if you compare that with the binding energy of the material, which is sitting, let us say, on compact star surface, you have 0.03% of rest mass is the binding energy of material on the white dwarf surface, but 15% of rest mass is the binding energy of material on neutron stars. So therefore, a thermonuclear power can actually eject material from the surface of the white dwarf, not quite eject material from the surface of the neutron star, but a small portion can be lifted, small fraction can be lifted, but most of it will still remain bound. So what happens and where does such a event occur? So if you have a white dwarf and if it is accreting material from a nearby star, it pulls material from the surface, hydrogen-rich material falls on the surface of the white dwarf, and because of a strong gravity, this material gets very dense and hot, and as that density and temperature reaches a certain critical state, thermonuclear fusion occurs. And once thermonuclear fusion occurs, you can get a runaway because matter is in degenerate condition, and you get a large amount of mass being thrown out because of this thermonuclear fusion. This is called nova explosions. A very similar process happens on neutron star surface, but because the neutron stars, because of neutron star strong gravity, not all the material is ejected. Maybe small skin is ejected, and the total amount of energy in each such thermonuclear explosion on the surface of the neutron star that is ejected is a small fraction of energy that is ejected in nova explosion. So it was 1,000th of that, because of most of it stays on the star and it falls back. But we do see these explosions both on white dwarfs and neutron stars. Now, if this donor object, as shown here, happens to be not a regular star, but another white dwarf, which is made primarily of carbon and oxygen, then the nuclear burning that happens as the material arrives is not strong enough to eject that material. So the mass of the white dwarf grows. As the mass grows, it will eventually go beyond the Chandrasekhar limit. As it goes beyond the Chandrasekhar limit, the white dwarf will condense, and that condensation will produce a lot of heat, and that will ignite the white dwarf, the entire white dwarf. The whole white dwarf will explode and produce something called a supernova.
Professor Bhattacharya, sorry to
Yes.
disturb you. 5 minutes maybe you can.
Oh, I see. Okay, so we're running quite late. Okay, so this is called type 1a supernova. So that's what we see from exploding white dwarfs. In case of another type of objects where you have a larger mass star to begin with, you have at the end of at the inner part of the star, you have iron that is produced, and nuclear burning keeps adding to the core of the star. The iron grows and again goes beyond the Chandrasekhar limit, then it collapses. As it collapses, a lot of gravitational binding energy is released, and a shock wave forms as it collapses very fast and bounces. And this shock wave can eject the entire external material, which is the envelope. And these are called supernovae of type 1, type 1b, c, and 2, not type 1a. This is wrongly typed here. And so these core collapse explosions are another type of supernova explosion where the total energy is actually even larger than the thermonuclear supernova. So 10 to the power of 46 joules, of which about 1% comes out in the electromagnetic radiation and kinetic energy. The rest goes out in neutrinos and gravitational waves. And in some of these explosions, you get a very powerful relativistically moving jet, which is ejected from the system. And if you happen to be looking straight into the throat of this jet, for example, towards the end of the simulation, you will see that, then you will see a very, very bright flash of gamma rays. And this is what is called a gamma ray burst. Similar, somewhat similar events can occur when two neutron stars can come together by merger, and due to gravitational waves. A lot of gravitational waves are released in this process. And again, a jet-like ejection occurs, and a gamma ray burst lasting a shorter time, less than 2 seconds, is produced. And the material that is ejected now is highly neutron rich. They undergo radioactive decay, power something called kilonova explosion, and produces heavy elements. Almost all our supply of heavy elements that we see in the universe, including all the gold and platinum that you are used to, could have been produced in explosions like these. Finally, when the material goes out, interacts with the matter surrounding the event, it produces these spectacular objects like remnants. So, remnants of supernovae, has seen many of them are known. Professor Yashwant Gupta told you about the Scrab Nebula, which is also a remnant of such a supernova explosion. And inside that, as you mentioned, there is a pulsar. The pulsar is producing charged particles right now, and then there is an extra emission. This diffuse blue emission inside is from those particles produced by the pulsar, and these filaments that you see is the remnant of the material that was ejected in the explosion. In other cases, where the central neutron star is either not there or its contribution is not apparent, you see this shell-type supernova remnants. These are very large, spectacular objects. An analog of that also happens in gamma ray bursts. So after the burst phase, you see this long-lasting afterglow, and these afterglows are relativistic analogs of such supernova remnants. These gamma ray bursts have been a subject of quite an intensive study in India as well. We have done a lot of work on gamma ray bursts using Indian telescopes. For example, the Nainital and Hanle telescope that were mentioned already in this workshop earlier, as well as GMRT. This is an example of a gamma ray burst which we worked on. Initially, we observed in optical, and for more than 6 years, we continue to observe it in radio, and we have acquired a wealth of information about this event as well as gamma ray bursts in general from these studies. These days, we have our own space astronomy mission called AstroSat. It has a detector on board called CZTI, which continues to detect a lot of gamma ray bursts. More than 500 gamma ray bursts have been detected till date, and from some of them, we are even able to detect the gamma ray polarization of so this is the first, and these are first detections of gamma ray polarization in this kind of waveband, and that gives us a lot of information about how the radiation is generated. The final thing I wanted to mention is that these explosions can be used to do cosmology, can tell us about the universe as a whole, because some of these explosions are so bright they can be seen to very large distances. Type 1a supernovae have been used as a distance indicator to calibrate the distance versus the expansion rate, the redshift, which gives us a measure of expansion rate. And from that, we have an evidence of dark energy, which many of you may have heard about. And gamma ray bursts, which are even brighter objects, can be seen to very large distances, redshifts exceeding 9. So within 500 million years of the formation of the universe after the Big Bang. And the rate of these objects give us an idea of how the star formation in the universe has changed over time. So it gives us a clue about the star formation history. So I'll summarize that from solar flares to gamma ray bursts, explosions are ubiquitous in the cosmos. Large explosions are caused mainly by thermonuclear runaway or gravitational collapse, and compact objects are involved in all of these. Explosions energize the diffuse gas and enrich it with heavy elements. Explosive phenomena are of key interest in multi-messenger astronomy, involving electromagnetic, gravitational wave, and neutrino detectors. The emergence of new tools is rapidly driving forward the science of transient sources, and this is one of the most active and promising branch of astronomy today. There is a strong Indian activity in this area, and excellent opportunities exist for young researchers to work on this theme. Thank you very much.
Thank you, Professor Bhattacharya, for a wonderful talk. And now we'll go for question answer sessions. So Bhaisak Palikan is asking, does the heat from the core of the Earth also act as thermal pressure apart from electrostatic repulsion?
Yes, it adds to the pressure, but numerically it's a small fraction of the total pressure. So the electrostatic pressure dominates.
Yeah. Now, Sri Sahai is asking, Sir, can you kindly explain about primordial black holes? They are formed in the early universe from elementary particles, but how are they different or significant with respect to other black holes?
They are no different from other black holes. The formation mechanism and formation epoch are different. The mass distribution could be different. They could have smaller masses, larger masses. We actually don't know exactly what is the mass distribution of primordial black holes. This is an active area of research. People are trying to constrain these masses. But in property, they are just the same as a black hole of that particular mass. There's nothing different between them and black holes formed at any other epoch.
Okay, so someone is asking, what are quantum black holes? Is there any such thing?
I'm not sure what that means. All black holes are quantum objects at some level. Okay. But there's nothing separate class of black holes called quantum.
Yeah, so you should be satisfied that all black holes are, in some sense, quantum mechanical property they have. Yeah. There's nothing different. So now next question is, sir, please explain about the magnetosphere which happens in radio burst.
Fast radio burst?
Happens in radio burst, he's saying.
I'm not sure about the context of the question.
Okay, so please explain about the magnetosphere which happens in the radio burst. I don't know.
Which radio burst? Are you talking about radio bursts like Jupiter's radio bursts? Yes, so those are magnetospheric phenomena. They are not explosive phenomena, so I didn't include them because they are also transients, but not explosive transients.
Okay, so are all the explosive events detected in space-time dependent, and can they be detected from archival data?
Oh yeah, there are many past explosions we continue to detect in archival data. Yes. So yes, they have not all been recognized when they actually occurred. So new analysis methods, more sensitive analysis of archival data are finding more and more historical transient events.
Okay. Now the next question is, micro black holes, also called mini black holes or quantum mechanical black holes, are hypothetical, tiny, less than 1 solar mass black holes for which quantum mechanical effects play an important role. The concept that black holes may exist that are smaller than stellar mass was introduced in 1971 by Stephen Hawking. Okay, he's saying, there is no question here there.
Yeah, that's fine. I mean, black holes can have any mass.
Yeah.
So what will happen is all black holes have a Hawking evaporation timescale.
Yeah.
It just depends on the mass. The larger the mass, the longer is the timescale. Yeah. But there is no qualitative difference between the black holes of different mass.
And the next question is, how supermassive black holes are so supermassive?
How do the supermassive black holes form? That is still not fully understood. But obviously, they start with somewhat smaller mass black holes, and their masses increase over time by accreting more and more material. So the details of this process are still being investigated.
Yes. So there are so many questions, but Dr. Parida, are you there? Or Dr. Devarati Roy? Our MSc, BSc students want to ask some questions directly.
So sir is asking, is there any question from this room?
Yeah, just switch on your camera. Switch on your camera, please.
Sir, there is no question from this room.
This side, okay. So anyone of
shall I stop sharing then?
Yeah, you can stop sharing. Panelists have any questions, please? Okay, there are a lot of questions, but we are running out of time. So let us thank once again to Professor Bhattacharya.
Thank you very much. In case you want to pick out some pertinent questions and send them to me later on, I can try to address them.
Sure.
Yeah,
So
very
we'll do
good,
that.
very good, very good.
Yeah. So we'll appreciate that if you do that.
We appreciate.
Yeah.
Thank you very much.
Yes, thank you very much.
Bye.
So, Professor Patrick Dasgupta, if you are online, can you please try?
Yes, I'm here, and if I'll try to share the screen.
Okay.
And Acharya is made my job somewhat easier.
Okay. Or will it be, I don't know, your sound is a problem. So if it doesn't work, then I was thinking if you talk on my phone and try to put the phone near here, and I just share your slides also. I will share the slides and you talk on my phone and try to put the phone on speaker mode and put it in the.
Is my audio still bad?
Yeah, audio is still lagging and it is breaking, vibrating.
Okay. Is my audio still bad?
Yeah, now it seems to be good. Let us try. And if it goes further bad, if it goes worse, then we will do that method.
Then probably I'll use the phone. So how do you plan to use? Yeah. Okay. First slide. Are you able to see?
First slide is visible. Please start.
Yeah. So as I had started earlier, the first radio burst that was identified, first fast radio burst that was identified was accidentally discovered by Lorimer and his team way back in 2007 when we was looking at the archival data. But of course, there are many bursts which have been discovered in real time, particularly telescopes like Parkes and Chime have contributed. And by now, there are about 820 fast radio bursts that have been discovered in the radio band between 400 megahertz to 2 gigahertz. And the dispersion measure for these bursts range from 110 to 3000 parsec per centimeter cube. Let me try to tell you a little bit about what dispersion measure is. Dispersion measure basically is the line of sight integral of the number density of the electrons. And why is it this important? Because the free electron density in the intervening plasma, what they do is the high frequency radio wave, they travel faster in this plasma while low frequency radio waves lag behind. It is a dispersive medium, therefore, and because of that, pulsars, the distances to pulsars can be measured, as Professor Dipankar has already described you about pulsars. One of the good way of measuring how far a pulsar in our galaxy is to look at the lag of low frequency radio signal from the pulsar compared to the high frequency radio signal. Let me illustrate to you with the Lorimer burst itself. So the Lorimer burst, as you can see, as a function of intensity of the radio signal, as a function of peak, and then of course there are these radio noise. If you look at the time of arrival of this single part, the function of the frequency, higher frequency signals, they arrive earlier, while low frequency signals, they later. And the delay is directly proportional to the simplicity of side path. Because the intergalactic medium is ionized, and so is a large fraction of interstellar medium, both the interstellar medium of our Milky Way galaxy and the intergalactic medium, which is lying between galaxies, and the large dispersion measure that is seen for these fast radio bursts, tell us that these objects are extragalactic. That is, these fast radio bursts are not happening in our own galaxy Milky Way, but they are happening in galaxies that are far away from Milky Way. What is characterizing the fast radio bursts are the millisecond duration of the radio transient. And by now, for this 820 fast radio burst, the time width of this fast radio burst range from about 0.2 millisecond to about 5,000 millisecond. And their flux densities range from about 0.04 to 200 Jansky. Now remember, Jansky was already introduced by Professor Yashwant Gupta. It is simply 10⁻26 watts per meter square per hertz. And the integrated flux density over their time duration, which is called fluence for gamma ray bursts, for fast radio bursts, because these are transient events. So one of the good way of characterizing is the time integral of the flux density over the transient event. And this fluence, which is integral of the flux density over the duration of the burst, for fast radio bursts range from about 0.02 Jansky millisecond to about 4,000 Jansky millisecond. What is very interesting is that while most of these fast radio bursts are one-time event, they have been detected just once. So there's a sudden radio emission, just like the pulse I showed, and then there's nothing. But about 24 FRBs detected so far, they exhibit repeating radio transients. That means consider one of the well-studied repeating fast radio bursts, 121102. This will be active and then disappear, and then after months, again, the recurring of the radio transients will occur, and so on. And the two well-known repeating fast radio bursts are FRB 121102 at a redshift of 0.193 and FRB 180814.J0422 plus 73 at a lower redshift, Z less than 0.1. Now here I must tell you what this redshift is. You know that the universe is expanding, and at any given time, the expansion is characterized by the scale of the universe. Today, if the scale is A0, then when the radiation started from a distant source, the scale would have been smaller, and let's say that scale is A1, then the redshift of such a source will be A0, that is scale factor today, divided by the scale factor at the time the signal started from the source to reach us today. So A0 divided by A1 minus 1, that is what is the redshift. Because the older interpretation of Hubble, that redshift is simply velocity with which the galaxy is moving away from us divided by the speed of light, that is no longer considered to be valid, because it is not the Doppler shift that determines the redshift. Rather, it is the expansion of the universe which leads to the space-time geometry, by virtue of Einstein's general relativity, the space itself is expanding. And because of that, any signal with a wavelength lambda, if lambda was the wavelength of the signal emitted from the source, by the time it reaches us, it is lambda 0, which is stretched out larger than original emitted wavelength lambda, because the universe itself is expanding. And therefore, you can see that FRB 121102 is nearly at a redshift of 0.2, which is more distant than FRB 180814, because its redshift is less than 0.1. Now, CHIMES, as I showed, has detected more repeaters, because thanks to CHIMES, we have 20 more repeaters that have been detected. And because radio telescopes are not all the time looking at the universe at all different angles, and the fact that you have already detected 820 FRBs, so therefore you can calculate what must be the true event rate, in order that when a telescope is looking at a particular direction, you pick up one fast radio burst. So that true event rate over all sky, if you estimate, it turns out to be 2000 FRBs per day. And these FRBs, this event rate is for somewhat brighter FRBs with fluence bigger than 2 Jansky millisecond. As I have already showed, that there are very bright FRBs, but there are also very weak FRBs, as weak as fluence being only 0.02 Jansky millisecond. So one has to explain any central engine that explains the fast radio burst. They have to also explain why is the event rate so high, 2000 per day. Another important characteristics which is seen for these FRBs is that FRBs have very large brightness temperature. And what is a brightness temperature? So the idea is that temperature, as you know, is well defined for any system that is in thermodynamic equilibrium. So black body radiation is nothing but a collection of radiation or photons that are in equilibrium with a thermal reservoir at some temperature T. So a black body at temperature T would have photons associated with it, whose distribution in energy is given by Planck spectrum as nu cube divided by e raised to power h nu by kt minus 1. That's the black body energy density, which is also called the Planck distribution. Now, you have many sources like pulsars, quasars. They are emitting copious amount of photons. And from that, if you ask the question that had these photons been coming due to a thermal body, what would be the equivalent temperature? All right. So what you're seeing is the flux density or flux from the sources. And you ask, if I'm measuring this flux or flux density, and if I assume that this is being produced by a black body, what would be the black body temperature? And that is what is called brightness temperature. And it turns out, if you calculate the brightness temperature for these transient fast radio burst, it turns out that the equivalent black body temperature is very high. It goes from 10 to the power 28 to 10 to the power 39 degree Kelvin. Sorry, this degree should have been before K. It has, due to a typo, it has come after K. So 10 to the power 28 to 10 to the power 39 degree Kelvin, and which basically means that the radiation cannot be thermal radiation. It is not incoherent radiation, but the radiation is very, very coherent. This also happens in the case of pulsars. For the pulsars also, if you estimate the brightness temperature for individual pulses, it turns out that the brightness temperature ranges from 10 to the power 33 to 10 to the power 35 degree Kelvin. And to explain why is pulsar radiation so coherent, you have to assume that the electrons that are going along the magnetic field lines, accelerated electrons going along field lines, the so-called curvature radiation scheme, it cannot be individual electrons unconnected with other electrons radiating. Rather, you should have a large number of electrons which are coherently going along the magnetic field lines and producing the energy. Oh, am I running out of time, Chiranjeev?
It is, just let me see. Still, you have time. 1610 by 1610. If you finish, it would be okay. But I'm just wondering, are you in the same slide for a long time? Because I don't see it is changing.
Yeah, exactly.